Hello there and welcome to Life Beyond Seen, where curiosity slows its breathing. The world gets a little quieter and science is allowed to unfold at a gentler pace. Tonight we are travelling to a place that most people will never visit. A place so cold, so remote and so difficult to reach that even now, with satellites overhead and machines under the sea, it still keeps its secrets with remarkable success. We are heading to the South Pole, or more accurately, to the vast Antarctic world that surrounds it, because buried under that immense white silence may be living things no human has ever seen. That is a strange thought, isn't it? In an age when people can watch volcanoes from space, order dinner from a phone, and complain about weak Wi-Fi while flying above the clouds, there are still corners of this planet where life may be moving in total darkness, untouched by cameras, nameless in every textbook, and entirely unaware that we exist. It is humbling in a rather healthy way. We tend to behave as though the Earth has already been catalogued, labelled and arranged into neat little drawers. Mammals, birds, fish, insects, fungi, all sorted and filed like socks in a very optimistic household. But the truth is messier. Nature has always been far less cooperative than our filing systems. Antarctica is especially uncooperative. From a distance, it can look simple. White ice, flat light, bitter wind. The kind of place that seems less like a landscape and more like a warning. It is easy to imagine it as empty, a frozen desert where nothing much happens except snow blowing sideways, and scientists walking very carefully while holding expensive equipment. But that impression is deeply misleading. Antarctica is not empty. It is hidden. There is a difference, and a rather important one. Under that ice, beneath shelves thicker than city blocks are tall, under floating platforms of frozen water, under snow that has compacted and hardened over timescales almost too large to picture, there are oceans, rock, sediment, trenches, lakes, microbial worlds, deep-sea floors, and ecological pockets that are not only difficult to reach, but in many cases practically sealed off from ordinary human observation. If you were designing a place for unknown creatures to avoid attention, you would struggle to do better. And so tonight, we are going to settle into that idea. Not in a rushed way, not as though we are trying to shout a documentary at your nervous system. There will be no frantic music, no dramatic narrator suddenly gasping that what scientists found next changed everything. We are simply going to take our time and move through this frozen world carefully, like someone walking into a dark room and letting their eyes adjust. Before we go any farther though, I'd love for you to pause for just a moment and think about where you are right now. Where in the world are you listening from tonight? What time is it in your corner of things? Is it late and quiet? Is the room dim except for a little light from a lamp or screen? Have you tucked yourself into bed already? Or are you listening from a sofa, or a train, or somewhere else you weren't expecting to end up when the day began? There is something I always enjoy about that. A story about one of the most isolated places on Earth can somehow gather people from kitchens, bedrooms, long roads, small apartments, and distant cities into the same slow moment. It is one of the more pleasant oddities of modern life, and certainly one of the less stressful ones. And if you find this kind of journey calming, or interesting, or simply a better alternative to staring at the ceiling, while your thoughts start reorganizing every awkward thing you've ever said since 2009, then I would be very grateful if you gave the video a like, and maybe subscribed as well. It really does help this quiet little corner reach more people who might need something slower at the end of the day. There is plenty of loudness in the world already. A bit more calm seems only fair. Now then, let us ease into the subject properly, because the South Pole has a very particular way of making the imagination work harder. Most of us grow up with a rough mental map of the world, and Antarctica usually enters it as the cold bit at the bottom. Penguins, icebergs, scientists in large coats. Perhaps a flag planted somewhere in a blizzard by a heroic person with very poor weather luck. It is not that any of those things are wrong. They are simply incomplete. The problem with Antarctica is that it resists easy summary. It is larger, stranger, and more active than the simplified version most of us carry around in our heads. To begin with, Antarctica is not just a sheet of ice sitting on top of a normal landscape. It is an entire continent covered by an ice mass so immense that it changes the very shape of the land beneath it. In places, that ice is several kilometers thick. That means there are mountains beneath it, valleys beneath it, sediment basins beneath it, and in some cases liquid water beneath it too. Some of that water is connected to the ocean. Some of it sits trapped in isolated lakes under the ice. Some of it may have been separated from the outside world for astonishing lengths of time. That alone should make a person sit up a little. Because once liquid water enters the picture, life enters the conversation. Perhaps not large life, perhaps not dramatic life, not at first. But life is persistent in a way that is frankly almost impolite. It appears in boiling vents, acidic pools, dry valleys, deep rock, salt brines, and undersea ice. Give it chemistry, give it a little energy source, give it something to work with, and it begins experimenting. It does not care whether the conditions are convenient for us. In fact, it almost seems to prefer when they are not. That is why the idea of unseen life near the South Pole is not some fanciful bedtime notion, assembled out of wishful thinking and a suspiciously cinematic soundtrack. It is a reasonable scientific possibility. In some cases, it is more than a possibility. Researchers already know that Antarctic waters contain extraordinary creatures, adapted to conditions that would kill or disable many organisms elsewhere. They have found fish with antifreeze proteins in their blood. They have found animals living under ice shelves. They have found ecosystems around hydrothermal vents in the Southern Ocean. They have found microscopic life in places once thought too extreme to support it at all. If such things can exist where we have looked, then the question naturally follows: what is living where we have not looked yet? And that question is much larger than it first sounds, because the difficulty is not just cold. People hear Antarctica and picture freezing temperatures, and yes, those are certainly part of the problem. The cold is severe enough to turn simple mistakes into emergencies, but from the perspective of exploration, cold is only one member of a very unpleasant committee. There is distance, there is darkness for long stretches of the year, there is sea ice that can shift and trap ships, there are storms, there is equipment failure, there is the challenge of drilling through thick ice without contaminating the very environments you're trying to study. There is the fact that some places are so remote and so logistically difficult that simply reaching them requires years of planning, enormous budgets, patient weather windows, and teams of highly skilled people who remain impressively calm while standing in conditions that would make most of us immediately reconsider our life choices. And even when scientists do arrive, what they can actually observe may still be limited. Cameras fail, water clouds up with sediment, ice blocks passage, sampling gear catches the wrong depth, the wrong patch of seabed, the wrong season. Imagine trying to understand an entire forest by lowering a bucket through a hole in the roof and hoping something interesting climbs in. You might learn something useful, certainly, but you would also miss almost everything. That is a useful way to think about Antarctica, not as a place we have fully explored and found only partly interesting, but as a place we have sampled in fragments. We know enough to be sure that it matters. We know enough to suspect that it is biologically richer and stranger than earlier generations assumed. We do not know enough to claim that its story is complete, and hidden life does not always announce itself in grand ways. Sometimes it first appears as a reading that should not quite be there, a chemical signature, a trace of metabolic activity, a cluster of microbes in a water sample pulled from somewhere thought nearly sterile. Sometimes it emerges as footage from a deep camera run, where a pale shape passes by just once and leaves everyone staring at the screen. Sometimes it turns up attached to ice, embedded in sediment, clinging to rock, or preserved in patterns that suggest an ecosystem rather than an accident. Science, despite the popular image, is often less like throwing open a door and more like noticing that someone has left muddy footprints in a corridor you thought was empty. What makes the Antarctic version of this especially compelling is the sheer scale of what remains difficult to inspect. Consider the underside of ice shelves, enormous floating extensions of glaciers that project out over the ocean. These are not little icy ledges. Some are vast, thick and hard to access from above or below. Beneath them are dark marine environments with low temperatures, unusual circulation and limited food input compared to open ocean waters. For years, people knew relatively little about what might live there simply because getting underneath them was such a challenge. Yet when researchers have managed to sample some of these places, they have found life. Not always abundant life, and not always large animals waving for the camera, but living communities nonetheless. That matters. Because every confirmed case of life in an extreme Antarctic habitat makes it a little harder to assume emptiness elsewhere. Then there are the subglacial lakes, bodies of water hidden under kilometres of ice. Some of these lakes have been identified through radar and other geophysical methods. They exist in darkness under pressure, isolated from ordinary surface conditions. If that sounds like the setup for a very expensive and very careful research program, that is because it is. But it also sounds like the sort of place where microbial life, at minimum, might survive if the chemistry allows it. And if microbes can survive, then the broader scientific imagination starts waking up. Not wildly, not irresponsibly, just enough to say, all right then, what else is possible? The phrase, "no human has ever seen," also deserves a little thought, because it can mean several things. It might mean a species that exists in a place no one has physically observed. It might mean a creature that has passed unnoticed in collected samples because it was tiny, difficult to identify, or mistaken for something familiar. It might mean an organism whose traces are known before the organism itself is ever properly imaged. Or it might mean a form of life that scientists predict should exist based on ecological conditions, but which remains undiscovered because no one has yet sampled the right place in the right way at the right time. Discovery is not always as clean as finding a neatly posed animal waiting under a spotlight. Often it is gradual, uncertain, and built from small pieces. Even large animals can escape notice longer than you might think if their environment is hard enough to access. We speak as though the planet has been visually inspected in full, as though somewhere there is a completed inventory with all the boxes ticked. But the oceans alone should cure us of that illusion. Vast parts of the deep sea floor remain poorly observed. New marine species are described every year. Some of them are small and obscure, some are large enough to seem like they ought to have introduced themselves much earlier. The combination of darkness, depth, cold, and inaccessibility is very effective at keeping secrets. There is also something quietly fascinating about the fact that Antarctica encourages a different pace of thinking. In many places, human beings can move quickly, survey quickly, build quickly, and assume that if something important were there, we would have noticed by now. Antarctica punishes that attitude. It does not yield to hurry. Machines have to be adapted. Field seasons are limited. Supplies must be calculated carefully. Waste has to be managed. Sterility matters. Safety matters. A storm can end plans in an afternoon. A frozen component can undo weeks of effort. It is science conducted in a place that does not care about deadlines and is unimpressed by confidence. That, strangely enough, is part of what makes it such a good setting for this subject. The possibility of unseen creatures feels believable there because Antarctica still has the physical power to keep people out. Not completely, of course. Human beings are persistent too, and sometimes a bit overproud about it. We return with better tools, better data, better vehicles, better drilling systems, better autonomous robots, better imaging, better sequencing, better questions. But every technical improvement also seems to reveal how much more there is to investigate. We solve one difficulty and find three more standing behind it with folded arms. It is tempting to imagine unknown Antarctic life in dramatic forms. A pale fish with impossible eyes. A translucent invertebrate drifting under black ice. A colony of microbes living on chemistry that would make a geologist grin in satisfaction. And some of those possibilities are grounded enough to deserve consideration. But one of the pleasures of this topic is that reality does not need embellishment to be interesting. The known Antarctic creatures are already unusual enough to reset expectations. When animals survive in water that would freeze ordinary tissues, when metabolism slows and adapts, when feeding strategies change to suit long darkness and sparse resources, when whole communities exist under conditions once dismissed as too extreme, then the threshold for surprise shifts. You start to realize that unknown creature does not necessarily mean monster, spectacle, or myth dressed in science clothing. It can simply mean an organism shaped by an environment few others can tolerate, living in a gap in our knowledge that still happens to be very large. Sometimes the most remarkable animal in the world is not the one with the biggest teeth. It is the one quietly getting on with life in a place where, by common sense standards, life should be making other arrangements. And perhaps that is the best way to enter this journey tonight. Not expecting fantasy, but expecting reality to be stranger than our first assumptions. Expecting patience to be rewarded. Expecting that the bottom of the world, far from being a blank white margin on the map, may hold entire stories that are still in the early stages of being read. So as the wind moves over that immense ice, and the sea below continues its cold and hidden circulation, and instruments lower down through drilled openings into black water no sunlight reaches, we begin with a simple idea. The South Pole does not mark the end of life. It marks one of the hardest places to look for it, and because of that, it remains one of the few regions on Earth where discovery still feels genuinely open-ended, where the next sample, the next dive, the next remotely operated vehicle, the next patient examination of a bit of sediment or a thread of DNA might reveal not merely a new data point, but a living thing that has gone about its existence for thousands, perhaps millions of years, entirely beyond human sight. That is where we are headed now, slowly and carefully, into a place that still hides more than it reveals. And to understand why that is, it helps to begin with the first great misconception people tend to bring with them when they think about Antarctica. The very ordinary but very misleading idea that a place so cold and white must therefore be empty. That misconception is easy to understand. Most people picture the South Pole and imagine a blank frozen plain where almost nothing can survive, let alone thrive. From a human point of view, it certainly looks unwelcoming enough. The temperatures are severe, the winds are sharp, the dryness is often overlooked, and the sheer scale of the ice makes the whole place seem stripped down to the bare minimum. There are no forests, no ordinary fields, no buzzing summer air full of insects making highly unreasonable demands on your personal space. If you glance at Antarctica from far away, it can seem less like a living continent, and more like the world has accidentally left the freezer door open. But that impression tells us more about human preferences than it does about life itself. We have a habit of defining a place as empty when it lacks the kinds of life we're used to noticing. Trees, birdsong, large mammals, bright flowers, things that move in obvious ways and present themselves politely at eye level. If those are absent, we tend to assume there is not much going on. Yet nature does not organise itself around our convenience, and Antarctica is one of the clearest examples of that. It is not empty at all. It is simply full of life that hides, endures, burrows, drifts, clings, sleeps, freezes without dying, or carries on in places we are not naturally equipped to inspect. There is also the small matter that when people say the South Pole, they often mean two related but different ideas at once. One is the geographic South Pole itself, the point at the southern end of Earth's axis, set high on the Antarctic plateau and covered by deep ice. The other is Antarctica as a whole, the vast continent and surrounding Southern Ocean. The actual South Pole inland is indeed one of the most extreme environments on the planet, and far less biologically busy than coastal Antarctica, or the waters around the continent. you're not likely to stroll around the pole itself and find bustling colonies of obvious animals going about their afternoon. Penguins, despite their reputation for excellent Antarctic branding, do not live at the geographic South Pole. They mostly stay much closer to the coast, which is quite sensible of them. Even the hardiest creatures have boundaries, and the middle of the polar plateau is not exactly inviting. Yet this distinction only strengthens the point. Antarctica can appear empty if you focus on the wrong layer or the wrong location. Stand on the high interior ice, and you may see almost nothing living in the ordinary sense. But that surface emptiness is not the whole story. It is the lid. Beneath it, around it, and along the margins, life has found ways to persist that are far more inventive than the simple image of a frozen wasteland would suggest. The continent itself is wrapped in systems that shift with the seasons. Sea ice spreads and retreats. Coastal waters bloom with microscopic life when sunlight returns. Beneath floating ice shelves, dark seawater moves slowly through hidden spaces. At the seafloor, communities of animals filter, scavenge, graze, and wait. In the thin summer windows where rock is exposed and conditions soften slightly, small pockets of terrestrial life wake up and get on with the difficult business of being alive. There are microbes in snow, microbes in rock, microbes in brine channels, microbes in lakes cut off under ice, and microbes in soils so cold and dry that one is tempted to apologize for even bringing them up. If life had a union representative, Antarctica would be a very convincing argument that management has ignored basic working conditions. The reason this hidden abundance matters is that it changes the way we ask questions. If Antarctica were merely barren, then the mystery would be simple. There would not be much to find because there would not be much there. But the truth is more interesting. We already know there is life in many Antarctic environments, and once that is accepted, the real puzzle becomes distribution. Where exactly is it? How much is there? How does it survive? What have we not yet sampled? Which habitats are sparsely occupied, and which only appear sparse because we have not looked with enough patience or the right tools? Those are much better questions than, is there anything there at all? Because they treat the continent as what it is, not a dead zone, but a place with difficult access and unconventional ecosystems. Take the Southern Ocean, for example, the waters surrounding Antarctica. From above, especially when ringed with ice, it can look still and severe. In reality, it is one of the most important marine systems on Earth. Cold and nutrient-rich waters support huge seasonal production of microscopic algae and other phytoplankton. Those tiny organisms, invisible to casual human eyes, form the base of food webs that support krill, fish, seabirds, seals, whales, and many lesser-known creatures living deeper down. This alone should be enough to retire the idea of emptiness. You do not get whales feeding in Antarctic waters because there is nothing there. You get them because, for parts of the year and in certain places, there is enough life concentrated in the cold to support some of the largest animals on the planet. Krill are a particularly good reminder that abundance does not always look dramatic from the human point of view. Individually, they are small crustaceans. Collectively, they are one of the great biological engines of Antarctic ecosystems. Swarms of them feed on phytoplankton and ice algae, and in turn they feed larger animals. They are not glamorous in the way a leopard seal is glamorous, if one can use that word for a creature that often looks as though it has opinions about your survival chances. Yet krill matter enormously. They are a good example of a life hiding in plain sight, present in staggering numbers but easy to overlook, because humans are not naturally impressed by small drifting crustaceans until someone informs us that entire food webs depend on them. Then there is sea ice itself, which many people imagine as a sterile barrier. It is not. Sea ice can contain tiny channels of salty liquid within it, especially as temperatures and salinity shift. These channels become habitats for microorganisms, including algae and bacteria. Ice algae grow on or within sea ice, and can be critical early-season food sources in polar ecosystems. Think about how peculiar that is. Even the ice, which seems like the most obvious symbol of lifelessness, can host communities. Not bustling little cities, certainly, but living systems all the same. The frozen surface is not merely a cap shutting biology out. In some cases, it is part of the habitat. That idea repeats itself across Antarctica. Layers that seem inert often turn out to be biologically active when studied closely enough. Rocks can contain microbial communities tucked inside tiny pore spaces, protected from some of the harshness outside. Cold desert soils, though sparse in visible life, may host bacteria, fungi, nematodes, and other hardy organisms adapted to minimal water and severe temperature swings. In a more temperate landscape, we might ignore such life because greener, louder organisms would steal the attention. In Antarctica, the small and quiet forms matter all the more because they reveal just how flexible life can be. There is a tendency, especially in popular imagination, to divide places into alive and not alive according to whether they resemble the environments in which humans feel comfortable. By that standard, Antarctica looks nearly vacant. By biological standards, though, comfort is not the main issue. Energy, chemistry, liquid water, timing, and adaptation matter far more. Where those ingredients appear, life tests the limits. Some Antarctic organisms have adapted to such cold conditions so specifically that warmer temperatures can actually stress them. That's a useful thing to sit with for a moment. We often talk as if cold is simply an obstacle to be overcome, as though life in Antarctica is always 1 degree away from total collapse. But many organisms there are not merely surviving cold by stubbornness, they are built for it. Their enzymes, cell membranes, growth rates, feeding patterns and life cycles are tuned to a place that would be punishing for outsiders. The cold is not just an enemy, it is part of the structure of the world they inhabit. This is where the idea of hidden creatures becomes especially sensible. When a place selects so strongly for specialized life, it tends to produce organisms that do not fit our standard expectations. Some Antarctic fish, for instance, produce antifreeze proteins that help prevent ice crystals from forming in their bodily fluids. Certain invertebrates tolerate freezing or dehydration in remarkable ways. Some microbes remain metabolically active at temperatures where most people would assume biology had politely excused itself from the room. These are not fantasy creatures. They are real examples of what selection can do in extreme conditions, and if the known organisms are already so unusual, then the unknown ones do not have to be impossible to be interesting. They only need to be local, specialized, and hard to find. Hard to find is Antarctica's specialty. One reason the continent hides life so effectively is that much of what matters is below the obvious surface. On land, the visible environment can be brutally sparse, yet below that lie ice sheets, subglacial water systems, buried sediments, and bedrock habitats. Offshore, the sea may be covered by ice for much of the year, and below that are layers of water with changing temperatures, salinities, currents, and food availability. Beneath floating ice shelves lie marine spaces that were inaccessible for most of human history and remain difficult to study even now. Farther down, the seafloor holds its own communities, many of them composed of animals that are not exactly household names. Few people casually discuss Antarctic bryozoans over breakfast, which is a shame, as it would improve certain breakfast tables considerably. These seafloor communities can be surprisingly rich. Sponges, worms, mollusks, crustaceans, sea stars, sea cucumbers, and other invertebrates inhabit Antarctic benthic environments, often with slow growth and long lifespans shaped by the cold. In some cases, because disturbances are infrequent and metabolic rates are reduced, Antarctic seafloor communities may develop structures and relationships quite different from their counterparts in warmer waters. Some animals become very large for their group, a pattern sometimes called polar gigantism. Not every species does this, but enough do that it has become one of those delightfully odd biological patterns that makes a person suspect the planet enjoys keeping a straight face while being quietly strange. Again, none of this matches the cliché of emptiness. It matches a place where life is present, but often hidden by scale, ice cover, darkness, or the limits of human observation. The seasons complicate matters further. Antarctic life is not distributed evenly through the year. Light returns and retreats. Productivity rises and falls. The food supply can be highly seasonal, especially near the surface. Animals breed, feed, migrate, or conserve energy according to those cycles. So if you visit or sample at one time of year, you may get a very misleading picture. A location that seems nearly empty in one season may be much more active in another. That is one of the difficulties in building a true picture of polar ecosystems. You're not studying a static display case. You're studying a place that changes dramatically with time, often on schedules that are not very convenient for field logistics. And field logistics in Antarctica are never convenient in the ordinary sense. Everything is harder there than people expect, including tasks that sound straightforward on paper. Deploy camera, collect water, drill access hole, send instrument down, recover sample. Those phrases look tidy in a project summary. In reality, each one may involve transport delays, weather setbacks, temperature-related equipment problems, safety concerns, contamination precautions, power constraints, communication issues, and a large number of professionals trying not to say anything impolite while handling metal objects in air that clearly does not support bare fingers for recreational purposes. Because the work is so difficult, our coverage remains patchy. Some areas have been studied far more than others. Some habitats are sampled intermittently. Some discoveries depend on chance. That patchiness matters. When humans say a place looks empty, we should ask whether the place is empty or whether our map of it is still full of holes. Antarctica is, in many ways, a masterclass in the difference. There is another layer to this, and it has to do with scale. Life can be hidden because it is deep, remote, or sealed off. It can also be hidden because it is small. Microbial ecosystems do not announce themselves with much fanfare. They do not wave from the horizon or leave obvious footprints. Yet in Antarctica they may be among the most important forms of life present in the harshest settings. Entire systems can depend on microscopic organisms processing nutrients, fixing carbon, surviving in thin films of water, or using chemical energy where sunlight is limited or absent. If your definition of meaningful life begins at the size of a rabbit, Antarctica will seem much emptier than it is. If your definition includes bacteria, archaea, microalgae, and tiny animals living at the edge of physiological possibility, then the picture changes immediately, and really it should. The history of science has repeatedly shown that the small things run more of the world than the large things do. Large animals may get the posters and gift shop magnets, but microbes have been doing the serious planetary work for a very long time. Even the bits of Antarctica that do support more visible life are often hidden from public imagination by geography. Coastal Antarctica, islands, polynyas, ice edges and productive marine zones are not what most people picture when they hear South Pole, yet they are essential to understanding the region's biology. It is a little like judging an entire city by staring only at the roof of one building. Yes, the roof may look sparse. That tells you almost nothing about the kitchens, stairwells, office gossip, or alarming number of mugs in the sink below. What scientists have learned over the past decades is that Antarctic ecosystems are often concentrated where conditions allow, structured by access to light, nutrients, open water, stable surfaces, or chemical energy. Life gathers where it can. It exploits windows of opportunity. It survives long dark intervals. It settles under shelves, around the ice edge, within porous rock, under snow, in sediments, and far below the waves. That distribution can make the whole region seem paradoxical. Enormous spaces look almost vacant, while nearby hidden pockets are biologically active. Once you accept that pattern, the phrase "not empty, only hidden" stops sounding like a dramatic line and starts sounding like a straightforward summary. It also sharpens the central mystery. If so much life can remain out of sight in environments we already know about, what else is still concealed in the environments we barely understand? What lies beneath thicker ice, farther from shore, deeper in sediments, in isolated water bodies under long-covered shelves, or in dark marine cavities never directly viewed? Which species have been sampled but not properly recognised? Which have left only genetic traces in water or mud? Which entire communities exist in places that no drill, camera or remotely operated vehicle has yet reached? That is not speculation for the sake of excitement. It is the normal consequence of studying a continent where access remains limited and known life keeps showing up in supposedly unlikely places. Perhaps the better way to say it is this: Antarctica does not lack life. It lacks easy visibility. Those are very different things. A quiet room is not an empty room if people are whispering in the dark. A locked house is not an abandoned house merely because you cannot see through the windows. The polar continent gives us that lesson again and again. What appears blank from above may contain structure below. What seems still may be circulating. What seems sterile may simply require finer instruments and more patience. That patience is beginning to pay off. Each year, with better sampling methods, better sequencing technology, better submersibles and more persistent field work, the old image of Antarctica as mostly lifeless becomes harder to defend. The continent remains extreme, certainly. Much of it remains brutally inhospitable by human standards. But hostile to humans is not the same as empty of organisms, and it never was. So when we continue deeper into this story, the question is no longer whether life can exist in the frozen south. We already know that it can. The more interesting question is where it lives when the surface tells you nothing. When the ice acts like a ceiling, and when an entire dark ocean moves below that ceiling out of sight, carrying with it the possibility that some of the most unusual creatures in Antarctica are not on the ice at all, but under it, in water no sunlight reaches. Once that surface illusion starts to fall away, Antarctica becomes much stranger, because the white lid people imagine as the whole environment is often only the top layer of it. Beneath parts of the Antarctic ice sheet and its floating ice shelves lies seawater. Moving through dark cavities no sunlight reaches at all. These are not tiny cracks with a bit of meltwater sloshing about. They are large hidden marine spaces beneath floating shelves of ice, places where ocean water circulates, melts ice from below, carries heat, salt, oxygen and particles, and creates one of the least observed habitats on Earth. British Antarctic Survey researchers have described floating ice shelves as the greatest unexplored habitat in the Southern Ocean, covering more than 1.5 million square kilometres of the Antarctic continental shelf, while a frontier study noted that the seafloor beneath floating ice shelves makes up roughly a third of Antarctica's continental shelf. That matters because most people still imagine the underside of Antarctic ice as blank and still, like the underside of a freezer tray, only much larger and considerably less convenient to inspect. In reality, an ice shelf is a floating extension of land ice, attached to the continent but spread out over the sea. Water can move beneath it for long distances. Sometimes that water is relatively cold shelf water. Sometimes warmer water masses find pathways into the cavity and increase melting from below. NASA has described deep channels beneath parts of West Antarctica that can funnel warmer water toward the underbelly of glaciers and shelves, and later work from NSF and other teams has shown that what happens below the ice strongly affects how the ice behaves above it. So the hidden ocean under Antarctic ice is not static scenery. It is active, structured, and important. From the point of view of light, though, it is an austere place. Sunlight does not penetrate hundreds of meters of solid ice. Under a thick shelf there is no open sky, no surface bloom directly overhead, no neat daily cue telling organisms when morning has arrived. Researchers who drilled through 900 meters of the Filchner-Ronner ice shelf reported complete darkness and seawater temperatures around minus 2.2 degrees Celsius. That is cold enough to sound like a clerical error if you're thinking in ordinary terms, but salt water can remain liquid below the usual freezing point of fresh water. So the environment under the ice is not just dark. It is dark, cold, pressurized, and often far from the nearest place where photosynthesis can happen. And yet, even there, life has been found. That is the detail that changes the mood of the whole subject. A habitat can be remote and severe and still not be empty. In 2021, a British Antarctic survey-led team reported the first record of a hard substrate community deep beneath an Antarctic ice shelf. The researchers had been drilling through the Filchner-Ronner ice shelf to collect sediment, hit a boulder instead, and lowered a camera. On that boulder, far under the shelf, they found stationary animals including sponges and organisms that may have represented previously unknown species. This was striking because prevailing ideas suggested that, as you moved farther from open water and sunlight, life under the shelf should become less abundant and simpler, especially for animals that feed by filtering food from the water. The numbers involved make the discovery even more remarkable. That borehole site was roughly 260 kilometers from the open ocean, and the team calculated that in terms of water flow, the community might have been as much as 625 to 1,500 kilometers from the nearest source of photosynthesis. That is an extraordinary supply line for any ecosystem. It is rather like discovering a village thriving at the end of a road you are not entirely sure existed, except the road is a current in total darkness under an ice shelf, and the village is made of attached animals filtering whatever usable material the water manages to deliver. The finding did not simply add one more odd species to a list. It forced researchers to reconsider the old idea that life beneath shelves must taper toward near barrenness the farther inland you go. This was not the first hint that under-ice marine spaces held more than expected. Decades earlier, work beneath the Ross ice shelf had already shown that animals could exist astonishingly far beneath the ice. A 1979 paper indexed in PubMed reported that baited traps and a camera lowered through the Ross ice shelf at a point 475 kilometers from the open Ross Sea and nearly 600 meters below sea level revealed fish, many amphipods, and an isopod. That is worth pausing over, because it reminds us that even in places where the seafloor looked soft and quiet, mobile animals were already there, moving through a habitat that most people would have written off as a biological dead end. Later observations and reviews continued to push that picture outward, with mobile life reported hundreds of kilometers under ice shelves. The real challenge, then, is not whether water exists under the ice. It does. It is not even whether some organisms can survive there. They can. The challenge is understanding how an ecosystem functions in a place where ordinary surface rules do not apply. In most marine environments near the surface, sunlight powers photosynthesis, phytoplankton grow, and the entire food web begins there. Beneath thick Antarctic ice shelves, that direct local production is absent. No sunlight means no local phytoplankton bloom overhead, so food must arrive from elsewhere or be produced in some other way. That simple fact is what makes these cavities so compelling. If life persists there, it has to solve the problem of energy in a way that is both efficient and patient. One solution appears to be transport. The BAS and Alfred Wegener Institute teams studying life beneath ice shelves concluded that enough algae and organic material can be carried under the shelf from open water to sustain surprisingly rich food webs. In the 2021 Current Biology report highlighted by BAS, the biodiversity of specimens collected from beneath an ice shelf was described as richer than many open water continental shelf samples, and the researchers argued that algae carried inward from open water must be fueling the system. Microscopy suggested some species were growing at rates comparable with open marine Antarctic habitats, and radiocarbon work on dead fragments indicated that life may have persisted there for nearly 6,000 years. Hidden does not necessarily mean starved. In some places, current-driven delivery seems to keep the pantry stocked well enough for communities to endure for millennia. That makes the under-ice ocean sound a little less like an isolated cave, and a little more like a concealed extension of the wider sea, connected by moving water even when it's shut off from light. The connection is important. Water masses flow beneath shelves, and those flows can be complex. They influence melting, salinity, oxygen distribution, and the transport of fine particles and food. Even when researchers are mainly interested in ice loss and sea level rise, the same physical circulation helps explain why some biological communities can exist at all. The under-ice cavity is not disconnected from the world beyond the shelf edge. It is simply hidden from direct view, with currents acting as the long, cold conveyor belts that link darkness to distant open water. There is a second possibility as well, and it becomes especially important when talking about environments farther inland under the Antarctic ice sheet rather than the marine cavities beneath floating shelves. In subglacial lakes, where there is no sunlight and often no easy delivery of fresh surface food, researchers have shown that microbes can use chemical energy instead of photosynthesis. NASA's astrobiology reporting on Lake Whillans described methane-eating microbes in the first sampling of a subglacial Antarctic lake, and noted that DNA data suggested thousands of species. BAS has likewise explained that in isolated subglacial lakes with no sunlight, microbes are thought to gain energy by processing chemicals concentrated in sediments, with geothermal heat helping drive convection and distribute oxygen and particles. So even beyond the ocean cavities under shelves, the broader hidden waters of Antarctica teach the same lesson. Remove sunlight, and life does not automatically quit. It changes strategies. Still, it would be wrong to imagine all of these under-ice worlds as interchangeable. A marine cavity beneath a shelf is not the same as an isolated subglacial lake. The marine cavity may receive inflowing seawater, suspended organic particles, and occasional animals moving with currents. A subglacial lake may be cut off for long periods and rely more heavily on geochemistry, sediments, and microbial processes. But they belong to the same general family of hidden Antarctic habitats, all united by darkness, cold, and the difficulty of access. That is part of why the South Pole region remains so scientifically tantalizing. There is not just one concealed environment under the ice. There are several, each with different rules, and each only partly observed. The difficulty of access cannot be overstated. A great deal of what scientists know about under-ice shelf biology has come from very limited windows. The Frontiers paper on the Filchner-Ronner discovery noted that before that study, observations of these habitats were restricted to what had been seen through just 8 boreholes, drilled mainly for geological or glaciological work. BAS described the total area previously studied beneath ice shelves as roughly the size of a tennis court. That is an astonishing sentence when set beside the total area hidden beneath Antarctic shelves. It means much of our current understanding comes from tiny punctures into an enormous concealed domain. If someone tried to explain an entire rainforest based on a few keyholes cut through the ceiling, we would call that obviously incomplete. Antarctica deserves the same honesty. It also means chance still plays a role. Some discoveries have come because a drill aimed at sediment hit rock instead. Some footage exists because a geological operation happened to carry a camera. Some hypotheses about what under-ice communities eat had to be revised because the communities turned out to be there in the first place, quietly refusing to conform to expectations. That kind of accidental discovery is not a sign of sloppy science. It is a sign of how young the exploration still is. When a habitat is hard enough to reach, even careful projects can end up making findings they were not originally designed to look for. Antarctica remains one of the few places where we were trying to do something else, and then found this, still appears regularly in serious research. There is something almost disorienting about the geometry of these places. In an ordinary ocean setting, We imagine the sea surface above, daylight filtering down, plankton near the top, and the seafloor below. Under a shelf, the ceiling is ice. The upper surface is solid and opaque. The nearest open water may be hundreds of kilometres away. The seafloor can still lie hundreds of metres lower. Animals may live attached to rocks in complete darkness, while mobile species swim through cold black water between them and the ice above. It is marine life, certainly, but in an upside-down sort of world, one where the usual cues are missing and the most important structures are hidden from anyone standing on the surface. The physical science of these cavities adds another layer of tension to the story, because the places most difficult to study are also places changing in response to climate. NASA reported that basal melt from underneath accounted for a large share of Antarctic ice shelf mass loss in the early 2000s, and more recent work continues to show that ocean-driven melt beneath shelves can thin and weaken them. That means the under-ice cavities are biologically intriguing not only because they are hidden, but because some are transient on human timescales. If an ice shelf thins, retreats, or collapses, the habitat beneath it changes as well. Organisms that evolved under darkness may suddenly find themselves under open water. New ecosystems may form in freshly exposed seafloor. Others may be lost before they are properly documented. The under-ice ocean is not just secret. In some places it is temporary. That creates a peculiar urgency. Scientists are trying to study ecosystems that are both remote and in motion. Some recent expeditions to areas newly exposed by iceberg carving or shelf retreat have reported rich seafloor communities and suggested that ocean currents may be supplying nutrients in ways not yet fully understood. Even when the exact sustaining mechanism remains uncertain, the pattern is becoming harder to ignore. Antarctic ice does not cover a lifeless void. Again and again, exploration reveals structured habitats, unexpected biodiversity, and organisms making a living in places our older models ranked near the bottom of the plausibility list. The map is not filling in with blankness, it is filling in with complexity. It also helps to remember that darkness in the ocean is not the same as death. Most of Earth's ocean volume is dark. Plenty of marine organisms are adapted to perpetual night, provided energy and chemistry cooperate. The Antarctic under-ice world is unusual, not because darkness alone is unheard of, but because the darkness is combined with severe cold, long distances from photosynthetic production, shifting circulation, heavy ice overhead, and extraordinary inaccessibility. Put all that together, and you do not get an impossible habitat. You get a habitat that selects strongly for specialists and hides them very effectively. That is exactly the sort of setting where human knowledge tends to lag behind reality. The phrase, "no sunlight reaches," can sound dramatic, but in this case it is simply literal. What is dramatic is what follows from it. Remove light and local photosynthesis, and you force ecosystems into dependence on transport, chemistry, recycling, patience, or some combination of all four. Remove easy access for human observers, and you allow those ecosystems to remain poorly known long after satellites have mapped the surface above them. Remove comfortable temperatures, and you narrow the field to organisms whose biology is fine-tuned for conditions most life avoids. The result is a hidden marine realm that feels almost theoretical until a drill breaks through, a camera descends, and something alive appears where a simple empty space was supposed to be. That is why the Antarctic under-ice ocean holds such a firm grip on the imagination. It is not merely dark water under frozen ceilings. It is a real world with structure, circulation, food pathways, seafloor habitats, and a biological story still being assembled from fragments. Every borehole, sediment core, water sample, camera drop, and robotic mission gives us another brief look through the lid. And each time, the same pattern emerges. The hidden ocean is less empty than expected, more connected than expected, and more biologically inventive than expected, which means the natural next step is not to marvel at the darkness itself, but to look more closely at the creatures built to endure it, because once seawater stays liquid at -2.2 degrees, and life still manages to hold on, the question becomes not whether organisms can survive in the coldest water on Earth, but how they do it at all. The hidden ocean beneath Antarctic ice sounds severe enough on its own, but the water itself is just as remarkable, because in parts of the Southern Ocean, the temperature can sit close to the freezing point of seawater, around minus 1.9 to minus 2 degrees Celsius. That is not the sort of cold most vertebrate life handles gracefully. For many fish elsewhere, tissues would begin to freeze, circulation would fail, and survival would become less a biological strategy and more a brief, administrative misunderstanding. Yet around Antarctica, whole groups of animals have spent millions of years adjusting themselves to precisely these conditions. British Antarctic Survey notes that nototheniod fish live in waters that can reach about minus 2 degrees Celsius, while research reviews describe Antarctic fish as living at ambient temperatures around minus 1.86 degrees Celsius and often within very narrow thermal ranges. That long exposure to cold matters because Antarctic marine life did not appear in a hurry and improvise its way through one unfortunate winter. BAS describes marine animals around Antarctica as having evolved in relative isolation for roughly 33.7 million years, after changes associated with the opening of the Drake Passage and the development of the Antarctic Circumpolar Current helped isolate the fauna near the continent and usher in a prolonged cooling of the Southern Ocean. Over that immense span of time, lineages that could not cope largely disappeared, while those that could endure and specialise persisted. The result is not a generic cold water fauna borrowed from elsewhere, but a community shaped by unusual stability, unusual isolation, and unusual selective pressure. The Antarctic marine world is not simply cold. It has been reliably cold for so long that many of its inhabitants are built around that fact in ways few other animals are. One of the clearest examples is the nototheniod fishes, the group that came to dominate Antarctic fish life after much of the older fauna was lost. BAS explains that these fish evolved antifreeze proteins that allow them to survive freezing waters, and multiple reviews describe those antifreeze glycoproteins as one of the central innovations behind their success in the Southern Ocean. By some estimates, notothenioids account for a striking share of Antarctic fish diversity and biomass, with sources describing them as making up about 90% of fish biomass in the region. That is not a minor side branch of fish evolution tucked away in a cold corner. It is a major reshaping of an ecosystem around an adaptation that sounds almost too neat to be real. Blood chemistry that helps stop lethal ice growth. Nature does occasionally show off when the setting is remote enough. The antifreeze story is fascinating, partly because it is not magic, only biochemistry doing a very difficult job. These proteins bind to tiny ice crystals and prevent them from growing in a way that would destroy cells and tissues. BAS and the Journal of Experimental Biology both describe them as essential protection in sub-zero Antarctic seawater. Later work from the University of Illinois team that studied notothenioids in McMurdo Sound added an even stranger twist. The same proteins that prevent freezing can also keep internal ice crystals from melting as easily as expected when temperatures rise. Their long-term record from one of the coldest marine environments on Earth found that seawater did not warm enough over 11 years to clear that internal ice completely. So these fish are not simply avoiding freezing once and carrying on. Some may be living with tiny persistent ice crystals inside them as a built-in consequence of surviving in water this cold. Adaptation, as usual, comes with a bill attached somewhere. Then there are the ice fish, which are unusual even by Antarctic standards and deserve their reputation as one of the oddest vertebrate groups on Earth. Smithsonian Ocean notes that Antarctic ice fish have no hemoglobin, the oxygen-carrying protein that normally makes blood red, and the Journal of Experimental Biology review likewise describes them as the only adult vertebrates known to have lost hemoglobin. This sounds like exactly the kind of plan a sensible fish should reject immediately, but the Southern Ocean is cold enough that it holds a great deal of dissolved oxygen, and scientific reviews describe these waters as highly oxygenated or near maximally oxygen saturated. In such an environment, thin, pale blood becomes possible, even if it would be absurd elsewhere. The fish have not broken the rules of biology. They have simply moved into a part of the world where a very different set of compromises can still function. This is one of the most useful things Antarctica teaches. The coldest water on Earth does not merely slow life down. It rewrites which solutions are worth keeping. In warmer seas, thick red blood full of oxygen-carrying cells is a tremendous advantage. In Antarctic waters, some species got by without it. In most oceans, freezing is a fatal boundary. In the Southern Ocean, antifreeze proteins turn that boundary into workable habitat. At the same time, these gains did not make the animals universally robust. BAS research projects and physiological studies repeatedly describe Antarctic marine species as highly adapted to a very stable environment and often stenothermal, meaning they tolerate only a narrow range of temperatures. In one bass-linked experiment, shallow marine environments with annual temperatures between about -2 and +2 degrees Celsius were used to study species vulnerable to small degrees of warming. In another bass experiment, a 1 degree Celsius rise in local sea temperature nearly doubled growth in a seabed community, showing how strongly even slight warming can alter biological responses. That narrowness is important because it reminds us that being exquisitely adapted is not the same thing as being invincible. Antarctic marine animals often live in one of the most thermally stable marine settings on the planet. BAS notes that some seabed communities experience annual temperatures varying only between about -2 and +1 degrees Celsius, and marine physiologists have argued for years that many Antarctic ectotherms live close to the edge of their performance window when it comes to warming. Their metabolism, oxygen handling, growth, development, and escape behaviours are tuned to remarkably cold, stable conditions. When the background changes even modestly, the consequences can be large, not because these animals are weak in some general sense, but because specialisation narrows flexibility. A creature built for a world that barely changes is often unusually sensitive when the world finally does. Still, daily life in Antarctic water is not only about fish. The seafloor beneath ice is full of slower stories. Smithsonian's overview of the Antarctic ocean floor describes the dark seabed beneath sea ice as covered with sea stars, urchins, ribbon worms and sponges, all feeding on whatever the cold system provides. The McMurdo Oceanographic Observatory, installed below thick sea ice in McMurdo Sound, was specifically created because this world is weird, rarely seen, and scientifically valuable. The images and long-term monitoring from under that ice have helped underline a truth that people standing on the frozen surface would never guess from appearance alone. The water below can hold a busy benthic community, one built not on speed and spectacle, but on patience. Life here often unfolds with the urgency of a very old librarian shelving books in a room where no one is allowed to run. That patience is not merely an impression. BAS reports that common Antarctic marine invertebrates use less energy to feed, grow and reproduce than their temperate and tropical relatives, and broader studies of Antarctic marine biology consistently describe slow growth, low basal metabolism, and reduced annual reproductive effort in many benthic animals. The cold slows chemistry, slows movement, slows development, and often stretches biological time into a longer form. An Antarctic animal may live for years or decades while investing in growth and reproduction at a pace that would seem almost leisurely in warmer waters. This is part of why these ecosystems can look deceptively quiet to us. Human beings are easily impressed by rapid motion, dense surface swarms, and obvious feeding frenzies. Antarctica often offers something else instead. Low temperature endurance, slow accumulation, and long-lived communities carrying on without much need for drama. Even so, the Antarctic does occasionally produce creatures that look as though someone increased the scale setting when no one was watching. Some polar animals exhibit what researchers call polar gigantism, and Antarctic sea spiders are one of the more unsettlingly elegant examples. The University of Hawaii reported that while most sea spider species globally are smaller than a fingernail, some Antarctic species have leg spans of more than a foot. That does not mean the Antarctic is full of enormous monsters striding about in the gloom, which would be inconvenient for everyone involved. It does mean that the combination of cold, oxygen availability, and evolutionary history can generate body sizes and forms that would seem improbable if we were judging solely by warmer seas. And in the dark under-ice habitats where divers and cameras occasionally meet these animals, they can look like the sort of discovery a novelist would be accused of exaggerating. The fish themselves are often no less remarkable for being subtler. The Journal of Experimental Biology review describes many notothenioids as benthic, often low metabolism fishes, with some species acting as sit-and-wait predators on the seafloor. They do not need to race constantly through the water column to prove their existence. They can conserve energy, use camouflage, and let the environment do some of the work. In a sea that stays cold all year, and where food supply may be seasonal or limited by ice cover, efficiency matters. A fish that moves less, spends less, and still survives is not lazy by Antarctic standards. It is sensible. Much of Antarctic evolution seems to reward sensibility over spectacle, which may be one reason humans underestimate the place. We are inclined to equate activity with significance. Antarctica often prefers quiet competence. There is also the simple physical strangeness of swimming in water this cold. University of Oregon, reporting on the McMurdo Observatory, described divers working in 28-degree Fahrenheit seawater below thick sea ice, and McMurdo Sound has long been recognised as one of the southernmost and coldest accessible marine settings on Earth. That helps explain why discoveries from there keep carrying a mild tone of disbelief even among professionals. If a habitat is cold enough that the sea can sit below the usual freezing point of fresh water, and dark enough that light is filtered or absent, and stable enough that annual variation is tiny, then any thriving animal community becomes inherently interesting. It is not that every Antarctic organism is bizarre in appearance. It is that the conditions themselves are so unforgiving by ordinary standards that even normal acts such as swimming, feeding, mating, or guarding eggs begin to look like small feats of engineering. That last point becomes especially vivid when reproduction enters the picture. In February 2024, University of Hawaii researchers reported solving a long-standing mystery about giant Antarctic sea spiders by observing how one parent attached eggs to the rocky bottom under ice, where they developed for months before hatching. The team noted that algae quickly overgrew the eggs and camouflaged them so effectively that they were hard to see even when the researchers knew their location. It is difficult to design a better example of how Antarctic life stays hidden. The creatures are there, the eggs are there, the entire process is happening, and yet the environment conspires with the animals to keep everything nearly invisible. This is not emptiness. It is concealment aided by cold, time, and excellent camouflage. The more one looks at Antarctic marine life, the clearer it becomes that survival in the coldest water is less about one grand trick than about a stack of compromises. Antifreeze proteins help, but they may leave persistent ice behind. High oxygen levels help, but they help to make bizarre blood systems viable only in this one kind of sea. Slow metabolism saves energy, but it often comes with slow growth and delayed development. Narrow thermal specialization allows fine-tuned performance in cold stability, but it can leave animals vulnerable to relatively modest warming. Nothing about these species suggests ease. What they show instead is balance. A long evolutionary negotiation with a harsh ocean in which every advantage appears to have been purchased with some limitation elsewhere. In that sense, Antarctica feels unusually honest. It does not hand out miracles, it offers deals. All of this should make us cautious whenever we use words like barren, empty, or lifeless for the polar south. The water under Antarctic ice may be among the coldest marine environments on Earth, but it supports fish that keep ice at bay, vertebrates with white blood, invertebrate communities that grow slowly and persist for years, and seafloor habitats busy with sea stars, worms, sponges, and other creatures most people never imagine while picturing a white horizon. The cold does not erase biology. It edits it, pares it down, stretches its timing, and rewards highly specific solutions. That is why the Antarctic marine realm continues to surprise scientists. It is not merely that animals live there, it is that they do so by means no one would confidently invent without first having seen them. And because so much of that life is slow, camouflaged, deep, or sealed away under ice, discovery often arrives in a slightly sideways fashion. A long-term temperature record reveals a physiological trade-off. A camera lowered through ice finds fish where almost none were expected. Divers studying one question notice a creature no one has fully understood for more than a century. A rock or sponge or patch of seabed appears on a monitor, and suddenly a whole new line of inquiry opens. Antarctica has a talent for that kind of revelation. It seldom throws open the door and announces itself. More often it lets people work very hard, look very closely, and then realise, almost by accident, that they have just found something astonishing. What makes Antarctica especially good at hiding life is not only the cold or the darkness, it is also the way discovery happens there. People do not usually stroll into the far south, lift a convenient flap of ice, and find a tidy creature waiting under a spotlight like it has been booked for a television appearance. More often, scientists go looking for one thing and find something else entirely. They drill for sediment and hit rock. They test a vehicle and discover an animal field. They arrive to study currents or geology, and the living world quietly appears in the edge of the frame, as though it had been there all along, which of course it had. That is one of the recurring patterns in Antarctic science. The continent does not just hide creatures from people who are searching carelessly, it often hides them from people who are searching carefully for something else. That accidental quality is worth dwelling on because it tells you something important about the place itself. In a well-mapped, easily reached environment, a great many biological discoveries come from direct surveys planned for that purpose. In Antarctica, by contrast, some of the most striking finds have emerged from geology programs, glaciology projects, drilling tests, and sudden opportunities created by shifting ice. British Antarctic Survey has noted that floating ice shelves cover more than 1.5 million square kilometres of the Antarctic continental shelf, yet only an area about the size of a tennis court had been studied through 8 prior boreholes at the time of one of its major under-ice discoveries. That is not the sort of sampling coverage that allows anyone to speak confidently about emptiness. It is the sort of coverage that encourages surprise. One of the earliest and most quietly remarkable examples came in 1977 beneath the Ross ice shelf. Scientists lowered baited traps and a camera through the shelf at a site 475 kilometres from the open Ross Sea and 597 metres below sea level. They were not entering a place that people expected to be lively in any obvious way. Yet the abstract of the published report notes that the equipment revealed fish, many amphipods, and one isopod, and that a fish was also caught through a crevasse 80 kilometres from the shelf edge. Those are plain words, almost modest words, but the implications are striking. Fish were present in dark water beneath an enormous ceiling of ice far from the open sea, in a place that could easily have been assumed nearly barren. The discovery did not arrive with fireworks. It arrived because someone lowered gear through a hole, and the hidden world answered back. There is something almost charming about how understated that older paper feels now. It does not behave as though it is narrating one of the great little shocks of Antarctic biology. It simply records what was found and lets the reader catch up. Fish, amphipods, an isopod, a soft bottom with lumps. That is often how science sounds when it has stumbled into something important before the wider imagination has had time to add dramatic music. But discoveries like that matter, because they loosen the hold of older assumptions. Once mobile animals have been documented that far beneath an ice shelf, the simple picture of under-ice spaces as lifeless storage compartments becomes much harder to maintain. It does not collapse all at once, but it starts to wobble, and Antarctica is full of scientific ideas that began wobbling before they fell over. A few decades later, another discovery arrived by way of a project that was not, at heart, a creature hunt at all. During the 2010 to 2011 Andril-Kuhlmann High Project fieldwork on the Ross Ice Shelf, teams were carrying out geophysical and environmental studies connected to geological drilling plans. The oceanography report on that work explains that hot water drill systems were used to open access holes through 250 to 275 metres of ice, and a remotely operated vehicle called Skeeny was deployed through one of those holes. According to the same report, this was the first time an ROV had been deployed through an Antarctic ice shelf. The researchers were there to characterise the sub-ice environment and support broader scientific objectives, not to stage a grand biological treasure hunt. Then the cameras went up under the ice, and the results, as the paper rather wonderfully puts it, were phenomenal. What Skinny found was not merely a stray animal passing through. It discovered and explored an unusual biological community dominated by anemones living inside burrows in the lower surface of the ice shelf itself. A later species paper in PLOS One states that exploration of the lower surface of the Ross Ice Shelf by Skeeny revealed a new species of sea anemone, Edwardsiella andrille, living in a previously undocumented ecosystem. The same paper explains that this species lives with most of its body embedded in the ice shelf, with only the tentacles extending into the seawater below, and that it was the first sea anemone reported to live in ice. That is the sort of finding that sounds like someone has rearranged the normal job description of a sea anemone without filing the paperwork. Sea anemones, broadly speaking, are not meant to improve the underside of an ice shelf for dramatic effect, and yet there they were. The details only make it stranger in a very satisfying way. The PLOS paper reports that upward-facing cameras on Skeeny captured a field of roughly 100 square metres inhabited by these small tentaculate animals, with a second field found about 6 kilometres away. The animals appear to live with most of their bodies inside the ice, while their tentacles dangled into the water below. The oceanography paper adds that the same broader survey also recorded an unknown organism nicknamed the egg roll, described in the figure text as hanging onto an anemone to maintain position in a current, and appearing to have appendages at both ends. There is something deeply Antarctic about that. Scientists go out to support geology and environmental measurements, run a vehicle under the shelf, and return with a new species, a field of animals living upside down in ice, and a drifting mystery object that had to be given a nickname because no one could sensibly introduce it otherwise. It also says a great deal about how little these habitats had been seen before. The PLOS paper notes that the biota associated with glacial ice was poorly documented because the habitat was largely inaccessible and technologically difficult to access. That sentence sounds obvious, but it is one of the key sentences in this whole story. Antarctica has hidden life not just because the life is rare, but because the habitat itself has been physically difficult to enter. In easier places, a strange sea anemone would likely have been discovered earlier, described earlier, and assigned a proper place in the literature without first requiring a hot water drill in a specialised under-ice ROV. Under an Antarctic shelf, it took all of that just to begin looking. Then came one of the best examples of serendipity in polar science, and perhaps the most famous one so far. In 2021, a British Antarctic survey-led team reported life beneath the Filchner-Ronne ice shelf after drilling through 900 metres of ice in the southeastern Weddell Sea. The press release states that the team had been carrying out an exploratory survey and that geologists drilling through the ice to collect sediment samples hit a rock instead of mud at the bottom of the ocean below. They lowered a camera and found a large boulder covered in strange creatures. At a site 260 kilometres from the open ocean, in complete darkness and at minus 2.2 degrees Celsius, they had discovered stationary animals such as sponges and potentially several previously unknown species attached to that boulder. It is hard to ask for a cleaner example of accidental discovery. They went for mud and found a community. British Antarctic Survey itself leaned into the accidental nature of the event, quoting lead author Hugh Griffiths, saying the discovery was one of those fortunate accidents that pushes ideas in a different direction. That is the right phrase for it. Before that finding, current theories held that life under ice shelves should become less abundant the farther one moved from open water and sunlight, and filter feeders in particular were expected to vanish first because they depend on food carried from above. The Filchner-Ronne boulder did not politely follow that script. Instead, it suggested that hard substrate communities could exist much farther beneath the ice than many people expected, and that unknown or poorly known species might already be doing quite well in a habitat humans had barely sampled at all. When a single mistaken encounter with rock can unsettle a whole set of assumptions, the habitat is still teaching us very basic lessons. That same year, another study added a different kind of surprise from beneath an ice shelf, this time under the Ekstrom ice shelf in the southeastern Weddell Sea. Bass reported that researchers from the Alfred Wegener Institute drilled 2 holes through nearly 200 metres of ice in 2018 and recovered fragments of seafloor life from a place several kilometres from open sea in perpetual darkness at about minus 2.2 degrees Celsius. What they found was not a lonely scrap of biology clinging on by its fingernails. The biodiversity of the specimens was described as extremely rich, in fact richer than many open water continental shelf samples. Microscopy showed that some species were growing at rates comparable to similar Antarctic shelf animals in open marine habitats, and radiocarbon dating of dead fragments suggested that this oasis of life may have existed continuously for nearly 6,000 years. That does not sound like a recent emergency workaround by a desperate ecosystem. It sounds like a long-established hidden community that simply had the good manners not to introduce itself until a drill arrived. The lesson that emerges from these under-ice finds is not merely that life can appear in strange places. It is that a great deal of Antarctic biology has been encountered sideways. Researchers have repeatedly gone out to study sediment, currents, ice, or drilling conditions and returned with evidence that animals were present in numbers or forms they had not expected. BAS summarised the Filchner-Ronne discovery by saying that only a tiny total area beneath ice shelves had been studied before, and the Ekstrom results further showed that collection, not just camera footage, can reveal communities much richer than assumption would allow. Antarctica, in other words, has not been taunting scientists with total invisibility. It has been allowing glimpses through very few holes, and even those glimpses have been enough to make older views look badly incomplete. Accident also enters the story in another way, through ice itself making decisions on its own schedule. In March 2025, Schmidt Ocean Institute reported that an international team aboard RV Falkor 2, originally in the Bellingshausen Sea to study the seafloor and ecosystem at the interface between ice and sea, rapidly changed plans after iceberg. A84 broke away from the George VI ice shelf on January 13th, 2025. By January 25th, the team had reached newly exposed seafloor that had never before been accessible to humans. The calving exposed about 510 square kilometres of seabed. Using ROV Sebastian over 8 days, the team found flourishing ecosystems at depths down to 1,300 metres, including large corals and sponges supporting icefish, giant sea spiders, and octopus, and they suspected that several new species had been discovered. That was not a discovery made because someone had neatly scheduled an appointment with the hidden seafloor. It happened because an iceberg the size of Chicago moved out of the way, and a research vessel was close enough, prepared enough, and sensible enough to seize the moment. There is something almost comical, in a very professional sort of way, about how often Antarctic discovery depends on this combination of patience and luck. Teams spend years preparing, budgets are arranged, equipment is tested, people travel to one of the harshest working environments on Earth, and then the most memorable biological moment arrives because the drill strikes the wrong thing, the camera points the right way, or a slab of ice leaves without consulting anyone's schedule. Schmidt Ocean Institute's own statement on the 2025 expedition described such moments as part of the excitement of research at sea. That is one way to put it. Another is that Antarctica continues to remind scientists that the planet is under no obligation to reveal itself in the order we would prefer. At the same time, it would be a mistake to think of these discoveries as random in the careless sense. They are not lucky accidents in the way one might find a coin down the back of the sofa. They are accidents made possible by preparation, technology, and persistence. The 2010 to 2011 Ross Ice Shelf anemones were seen because teams had hot water drilling systems, a specialised ROV, and the willingness to put all of it to work under a shelf. The Filchner-Ronner sponges were found because geologists drilled 900 metres through ice and lowered a camera rather than simply complaining about the boulder and going home. The 84 ecosystem was documented because a ship with ROV capability and a flexible science team could pivot quickly when conditions changed. Antarctica may hand out surprises, but it tends to reserve them for people who have done an unreasonable amount of homework. What these incidents also reveal is how often Antarctic life first enters human awareness as fragments: a fish in a trap, amphipods in a camera frame, a field of unfamiliar animals hanging from ice, dead bryozoan fragments suggesting a long-lived hidden oasis, a boulder with attached sponges where mud was expected, a newly opened seafloor scattered with organisms that seem to have been there for decades or centuries. Discovery often starts not with a full ecosystem neatly explained, but with a clue that refuses to fit old expectations. The explanation comes later, if it comes at all. That is especially true under Antarctic ice, where supply lines, food webs, currents, and life histories are often still being worked out after the first organisms have already been filmed or collected. In that sense, Creatures We Found by Accident is not just a collection of entertaining anecdotes, it is a description of the current state of knowledge. The far south remains undersampled enough that major biological findings can still emerge from side doors. That is unusual in a world where people sometimes speak as though every large mystery has already been reduced to paperwork. Antarctica resists that mood. It still allows the kind of moment when a team peers through a new opening and realises that an entire biological assumption has just become less secure. It still produces the quiet astonishment of finding life where theory had predicted very little, or finding unfamiliar life in a place barely observed before. That is not because science is failing there. It is because science is still early there, and perhaps that is why these discoveries are so satisfying. They are not tales of fantasy creatures leaping out of myth. They are better than that. They are real animals in real habitats, found by real people who are often trying to do something entirely different, and who were then forced to pause and admit that the hidden south had once again proved less simple than expected. Fish under shelves, amphipods far from open water, a sea anemone living in ice, sponges on a boulder under nearly a kilometre of frozen cover, corals, sea spiders, and octopus revealed only because a great slab of ice had finally moved away. One by one, these findings build a picture of Antarctica not as a blank place, but as a place that keeps being caught in the act of being alive. Once you see the pattern, the next step feels inevitable. If so many discoveries have come from accidents, side missions, sudden breaks in the ice, and a very small number of holes in very large shelves, then the real mystery is not whether Antarctica hides more life. It plainly does. The deeper mystery is how much of that life is still waiting in places hardly any human has touched at all, especially on the Antarctic seafloor, where the dark stretches far beyond the edge of the drill hole, and the number of direct human visits remains vanishingly small. Once you accept that life can persist in the coldest seawater on Earth, the next adjustment is realising how little of its actual home we have really seen. The Antarctic seafloor sounds like a single place, but it is not. It includes a very deep continental shelf, steep slopes, abyssal plains, troughs, basins, canyons, seamounts, and ice shelf cavities, all spread across a region so large and so difficult to reach that even the maps are still being corrected. A 2025 scientific report study presented a new Antarctic bathymetry, because many continental shelf areas and ice shelf cavities were still incomplete or previously unmeasured, and NOAA notes that, globally, even with satellite coverage and ship surveys, only 27.3% of the seafloor had been mapped to modern high-resolution standards by June 2025, while explorers had visually seen less than 0.001% of the deep sea floor. That is a global figure, but it helps explain why direct visual knowledge of the Antarctic deep bottom is still so thin. Antarctica makes that problem worse in very practical ways. Sea ice blocks ships. Icebergs ground on the shelf. Weather shortens field seasons. Much of the bottom lies under water that is permanently dark at depth, and some of it lies beneath floating ice shelves, which means it is hidden even from the ocean surface above. The 2025 Antarctic bathymetry paper explains that ice-breaking ships with multi-beam sonar are the main way bathymetry is measured, but extensive sea ice cover and stranded icebergs make navigation difficult, leaving vast Antarctic territories without seafloor soundings. The same paper notes that mapping beneath ice shelves is even harder, often requiring seismic work, autonomous vehicles, or measurements through boreholes, and that adequate coverage was lacking for all but 8 of the 160 largest ice shelves. So when people imagine the deep Antarctic seabed as a place a few scientists have already walked all over, they are imagining a world that does not exist. The shape of that sea floor is unusual even before the ice gets involved. Reviews from BAS and Frontiers describe the Antarctic continental shelf as far deeper than most continental shelves elsewhere, averaging roughly 450 to 500 metres and exceeding 1,000 metres in places because of long-term glacial erosion and the weight of the ice depressing the crust. The Ross Sea Shelf alone covers about 466,000 square kilometres and is the largest and widest in Antarctica, while the Southern Ocean as a whole contains about 4.59 million square kilometres of shelf, 2.35 million square kilometres of slope, and roughly 27.9 million square kilometres of deep sea below 3,000 metres. In other words, much of the Southern Ocean floor is genuinely deep, and the Antarctic shelf itself is already deep enough to behave differently from the shallower continental margins people may have in mind. That size is one reason the phrase "few humans have touched" is not an exaggeration. In practice, most encounters with the deep Antarctic bottom come through towed cameras, multicorers, beam trawls, submersibles, or remotely operated vehicles, not through people physically going down there. The Ross Sea Benthic survey published in Frontiers in Marine Science sampled shelf, slope, and abyssal habitats using video, trawls, and multicorers, including previously unsampled habitats on the northern continental slope and abyssal plain. The BAS story on the 2012 East Scotia Ridge Vent expedition noted that the first survey of those Antarctic vents used an ROV because at 2.5 kilometres depth it is totally dark and the vehicle's lights only give visibility for a few metres. The Antarctic deep sea floor is usually not a place humans visit in person. It is a place humans glimpse by proxy, a little rectangle of light moving through black water. And when those glimpses arrive, the seafloor often looks far less empty than distance and darkness would suggest. The Ross Sea survey found clear differences between shelf, slope, and abyssal communities, with more diverse substrates on the slope and abyss, higher overall taxonomic diversity on the shelf, and shifts in feeding modes across environments. Mega-epifauna on the shelf and slope were dominated by suspension feeders, while deposit feeder grazers became more prominent in the abyss. That matters because it shows the bottom is not one bland field of mud occupied by interchangeable animals. It is structured, patchy, and responsive to depth, food supply, ice conditions, and circulation. Even within one Antarctic region, the seafloor changes from place to place in ways that alter who can live there and how. A great deal of this complexity remained hidden simply because deep Southern Ocean biology was sampled so sparsely for so long. The Deep Southern Ocean Benthos Review in Philosophical Transactions of the Royal Society B states plainly that few investigations of deep-sea biology had been carried out in the Southern Ocean, and that none had been devoted exclusively to the deep water before more modern expeditions. It describes ANDEEP, carried out in 2002 and 2005, as the most recent and extensive biological deep-sea survey in Antarctica at that time, based on about 40 stations. Even that sounds modest when set against the size of the region. 40 stations in a place this large is not comprehensive knowledge. It is the beginning of acquaintance. What made ANDEEP so important is that it immediately hinted at how much novelty had been sitting down there waiting. Bass's summary of the 2008 Nature paper on the deep Weddell Sea and adjacent areas reports sampling from 748 to 6,348 metres, and notes the discovery of high levels of new biodiversity, including 674 isopod species, of which 585 were new to science. The broader review adds that in many taxa, far more than 90% of the species collected in a typical abyssal sediment sample are new to science, though that partly reflects how undersampled these regions are. Either way, the result is the same. The Antarctic deep sea floor is not interesting because it contains one or two odd animals tucked away in corners. It is interesting because whole stretches of its biodiversity inventory are still incomplete. That incompleteness is not evenly distributed across all kinds of life. Some groups are better known than others, and some habitats are better sampled than others, but the general pattern keeps repeating. The 2006 review describes Antarctic deep-sea biodiversity as scarce in knowledge overall, notes that records for many groups are still limited at abyssal depths, and points out that patchiness and rarity are hard to interpret because of limited sampling. A later 2014 review on the challenges of Southern Ocean deep-sea biodiversity assessments emphasised geographical sampling bias, depth-related faunal gaps, and limited understanding of species patchiness and rarity. So when a sample comes up holding a new or poorly known species, that does not necessarily mean the organism itself is exceptionally rare. Sometimes it simply means no one had sampled that patch of bottom carefully enough before. There's also a strong tendency to imagine the deep Antarctic bottom as uniformly soft, flat, and biologically subdued. Parts of it are soft and flat, certainly, but the larger region contains much more than that. BAS and other reviews describe canyons, seamounts, reefs, hydrothermal vents, and faulted terrain across the Southern Ocean deep sea. The 2025 bathymetry paper reports previously unknown troughs and deeper channels in many parts of Antarctica, especially East Antarctica, implying that some regions are more open to deep water exchange than earlier maps suggested. That is important not only for ice melt and oceanography, but also for life. Seafloor shape controls currents, sedimentation, food delivery, and habitat type. A trough, sill, ridge, or seamount is not just geology. It is often the reason one biological community forms here, and a different one forms a little farther away. Some of the most dramatic examples come from hydrothermal vents near Antarctica, where the seafloor is not merely dark and cold, but also locally heated by geology. In January 2012, BAS reported that ROV surveys on the East Scotia Ridge discovered communities of species previously unknown to science around Antarctic hydrothermal vents, including a new species of yeti crab, starfish, barnacles, sea anemones, and an octopus. The team noted that the vent field lacked several familiar vent animals seen in other oceans, suggesting the Southern Ocean can act as a barrier and foster distinct communities. Later work on the East Scotia Ridge described those vents as the first explored in the Antarctic and documented dominance by large peltospiroid gastropods, stalked barnacles, and Kiwa yeti crabs. So even where the Antarctic deep bottom resembles other deep oceans in having vents, it does not simply repeat their cast of characters, it does its own version. That point was reinforced again in 2025 at the South Sandwich Islands. Schmidt Ocean Institute reported that a 35-day expedition explored one of the most remote island chains in the world and found coral gardens, hydrothermal vents, and many suspected new species, including corals, sponges, snails, sea urchins, benthic ctenophores, and sea stars. The team also documented one of the shallowest hydrothermal vents known near the islands at about 700 metres depth and explored the South Sandwich Trench, described as one of the coldest and most isolated submarine trenches on the planet. One especially odd observation was snailfish eggs laid on a black coral, a previously unknown behaviour according to the expedition report. That is a very Antarctic kind of finding. Not merely a new species, but a new bit of animal behaviour discovered in one of the least visited corners of the Southern Ocean. The deep Antarctic seafloor is also full of organisms that do not attract much attention until someone finally sends a camera down and sees how large or how old they may be. In March 2025, after Iceberger 84 carved away from the George VI ice shelf, Schmidt Ocean Institute and BAS reported flourishing ecosystems on the newly accessible seafloor at depths down to 1,300 metres, including large corals and sponges supporting icefish, giant sea spiders, and octopus. Scientists involved in the expedition said, based on the size of the animals, that the communities may have been there for decades or even hundreds of years. Another 2023 assessment of Southern Ocean vulnerable marine ecosystems notes that a significant share of the region's seafloor biodiversity is associated with fragile, slow-growing, long-lived, habitat-forming taxa. In other words, some of the Antarctic seabed is not simply alive, it is quietly ancient. This makes the Antarctic bottom unusually easy to damage and unusually slow to recover. Frontier's 2021 review on Southern Ocean seafloor habitats warns that vulnerable species include slow-growing habitat formers such as sponges, bryozoans and corals, especially where warming, acidification, fishing pressure or other disturbances operate. The 2023 ICES paper similarly frames many Southern Ocean benthic assemblages as vulnerable marine ecosystems because they are dominated by fragile, long-lived, and slow-growing epibenthic organisms that can be altered permanently by short-term or chronic disturbance. That means every new camera transect is doing two things at once. It is revealing life, and it is also showing why so much caution is needed once that life is known to be there. In some habitats, a trawl, anchor, or abrupt shift in conditions could erase structures that took decades, centuries, or longer to assemble. The Ross Sea is a particularly good case study because it combines relative protection with large gaps in direct deep-bottom knowledge. The 2021 Ross Sea paper describes the region as one of the least human-impacted marine environments in the world, largely because its remoteness, intense seasonality, and extensive ice cover make access difficult. Yet the same paper states that while the shelf fauna is comparatively well known, the slope and abyssal environments have had little scientific study. That contrast is almost the whole Antarctic story in miniature. We know enough to say the ecosystems are important, diverse, and in some areas relatively intact. We do not know enough to pretend the map is complete. The places with the fewest people on them often also have the weakest baseline. It helps too to remember that seeing the seafloor is not the same as understanding it. Sonar can sketch topography. A camera can show a few meters at a time. A trawl can bring up a sample, though often at the cost of context. A multicore can preserve sediments and fauna from a very small patch. Each method is useful, but each is partial. NOAA points out that seafloor maps can indicate features and potential habitats, yet they cannot identify species or show how organisms interact. The Antarctic seafloor remains especially difficult because many of its important habitats are patchy. A coral garden, sponge field, vent assemblage, soft sediment community, or rocky outcrop may occupy one section of bottom, while a neighbouring section looks entirely different. Sampling one does not automatically explain the other. That is why the phrase, "few humans have touched," can be taken almost literally, but should probably be understood more broadly. Very few people have ever been physically present at these depths in Antarctic waters, and even fewer parts of the seafloor have been closely observed. But the more important point is that the deep bottom remains thinly experienced, even through machines. A region can be mapped in broad form and still be biologically unfamiliar. It can be sampled at a few stations and still remain ecologically mysterious. Antarctica offers this lesson over and over. A charted area is not the same thing as a known area. A sounding is not the same thing as a story. And a black and white contour line on a map tells you nothing at all about whether a sponge, a sea star, a worm, or an entirely undescribed crustacean is living there in the dark. There is also a quieter reason the deep Antarctic floor stays hidden. Its most interesting places are often revealed only when ice, weather, or logistics allow a narrow opening. A carved iceberg exposes a new stretch of bottom. A research vessel gets one precious season of access. An ROV survives a difficult dive window. A borehole reaches water. A trench, seamount, or vent field appears on a map detailed enough to justify a closer look. BAS's 2012 vent report makes clear how much navigation depended on improved seabed mapping before the ROV could even move safely around the site, and the 2025 South Sandwich Expedition report shows the same pattern, with mapping data first identifying pockmarks that were then investigated with Sebastian to confirm hydrothermal vents. In Antarctica, seeing the bottom often requires first guessing very carefully where the bottom will reward the effort. For a long time, this kind of difficulty encouraged a misleading image of Antarctica as a place where the biological headlines all belong to the surface. Penguins, seals, whales, krill, sea ice. Those are real and important, of course, but the more the seabed comes into focus, the more obvious it becomes that a large part of the Antarctic story has been unfolding below the level most people ever think about. There are rich shelf communities, poorly known abyssal plains, unique vent provinces, newly exposed bottoms under former ice, and deep habitats where the species list is still very much under construction. BAS summarised the 2008 deep sea findings by saying that the Southern Ocean deep sea showed high levels of new biodiversity, and later assessments have only strengthened the view that the benthos is both richer and more heterogeneous than older assumptions allowed. So the deep Antarctic sea floor remains one of those rare places on Earth where serious science still carries a strong chance of basic discovery. Not because people have been lazy, and not because the organisms are necessarily trying especially hard to be mysterious, but because the setting itself has done most of the hiding. Darkness hides, ice hides, distance hides, slow growth hides, patchiness hides, limited ship time hides, a huge shelf and vast abyssal plain hide. And when the hiding is that effective, the next major finding does not need to be a giant creature to matter. It may be a new species in a core, a vent community unlike others elsewhere, an unexpected nursery behaviour in a trench, or a seafloor oasis that sat under ice for centuries before a single camera finally arrived. And once you start thinking that way, the seafloor stops looking like the end of the story and starts looking like a threshold. Because even farther inland, beyond the open Southern Ocean, and beyond the visible shelf edge, Antarctica hides another set of waters that are harder to imagine still. Lakes buried under kilometres of ice, sealed off from daylight and weather, carrying the possibility that some of the most isolated life in the south is not on the seafloor at all, but locked away inside the continent itself. Farther inland, away from the shelf edge and away from the seafloor communities under the ocean, Antarctica keeps another kind of secret. The water does not always stay in the sea. In some places it gathers beneath the ice sheet itself, forming lakes under hundreds or thousands of metres of ice. These lakes remain liquid because pressure lowers the freezing point, geothermal heat rises from below, and the immense ice above acts as insulation rather than simply as a lid. NASA's astrobiology reporting on Antarctic subglacial lakes notes that lakes such as Mercer can remain below 0 degrees Celsius, yet stay liquid under more than a kilometre of ice, and it describes the broader category of subglacial lakes as one of Earth's most difficult environments to access. For a long time, those lakes sounded almost speculative, the sort of thing one might mention with a raised eyebrow and a careful voice, as if the continent itself were making an implausible suggestion. But they are real, and the inventory keeps growing. A 2025 Nature Communications paper, using a decade of Cryosat-2 data, identified 85 new, active Antarctic subglacial lakes, increasing the known number of active lakes from 146 to 231, and bringing the total number of subglacial lakes in Antarctica to 766. That matters because it changes the scale of the story. We are not speaking about one odd lake hidden under one lucky patch of ice. We are speaking about a vast buried hydrological world beneath the continent. That hidden world is also more complicated than the popular version usually suggests. People often imagine every buried lake as a sealed vault, untouched for unimaginable spans of time, sitting in total silence while the ice above ages by millennia. Some of them may be close to that image, many are not. The 2025 study describes active lakes that fill and drain over multi-year cycles, often linked to subglacial hydrological pathways and fast-flowing ice streams. NASA's astrobiology overview makes the same point in simpler terms, explaining that not all Antarctic subglacial lakes are completely isolated, and that some are part of a vast drainage system beneath the ice. So the subglacial world includes both long-sealed pockets and more dynamic waterways, which is exactly the sort of detail Antarctica likes to hide until someone measures it properly. This is where the phrase, buried under ice for millions of years, needs a little care. It is not wrong, but it is not equally true for every lake. NASA's 2017 astrobiology feature states that some Antarctic subglacial lakes have been sealed off from the outside world for millions of years, while an NSF overview says that although not yet confirmed, some may have been isolated from the atmosphere for as long as 25 to 35 million years. At the same time, other lakes are clearly active parts of moving drainage systems. In other words, Antarctica contains both ancient sealed rooms and rapidly changing plumbing. It does not offer one neat category. It offers a buried landscape of different ages, different connections, and different kinds of mystery. That distinction becomes very clear when you compare the best-known lakes. Lake Mercer, in West Antarctica, is a good example of a lake that is hidden, but not truly cut off in the absolute sense. NASA's 2022 astrobiology feature says Mercer covers about 160 square kilometres, is around 15 metres deep, lies below roughly 1,067 metres of ice, and is connected to a broader hydrological system. The same source notes that scientists think the water in Mercer could be replaced with water from the ocean over a period of about 10 years. A 2023 study on Mercer sediments went even further, estimating that the lake itself may have formed only 53 to 260 years before the sediment core was recovered, with a most likely age of about 180 years. That is not a fossilized time capsule from deep geological antiquity. It is a modern lake in a moving system, hidden under a kilometre of ice but still caught up in the continent's shifting internal plumbing. Mercer is useful because it prevents the imagination from wandering too far into the wrong kind of romance. Not every buried lake is a little bottle of ancient darkness with the cork never pulled. Some are far more dynamic than that. Yet even the dynamic lakes are extraordinary. The SALSA project drilled more than 1,200 metres through the ice above Mercer in 2018 and 2019. Not because the lake was expected to contain a parade of spectacular creatures, but because even a young or connected subglacial lake can reveal how life and chemistry function where sunlight never arrives, and ordinary food supplies are scarce. NASA's account emphasises that these projects require careful, clean drilling and advanced instruments simply to enter the water without spoiling it. That alone explains why such lakes can remain scientifically mysterious even after satellites have traced the continent above them in impressive detail. Lake Whillans offers a different kind of landmark in this story because it was the first Antarctic subglacial lake to be cleanly sampled directly. NASA's 2017 astrobiology feature says the Wizard team drilled 800 metres through the West Antarctic ice sheet into Lake Whillans, extracted water and sediment, and found highly efficient methane-eating microbes. It quotes project lead John Priskew saying he was not surprised to find life, but he was surprised by how much life there was. According to the same report, DNA sequence data suggested about 4,000 species, and the lake held enough dissolved organic carbon and chemical energy that the system seemed more biologically active than many people had expected. That is one of the quiet shocks of the Antarctic interior. Even in a buried lake under dark ice, the problem is not always whether anything's alive. The problem is whether we have been underestimating how much can be alive there. Lake Whillans also changed the tone of the entire discussion because it moved the idea of life in subglacial lakes from plausible speculation to direct observation. NASA's 2013 report on the first view, below the ice of Lake Whillans, says the team identified living cells in the samples, confirming that life can survive in deep, dark subglacial lakes. Later work summarised by NASA in 2017 explained that methane concentrations in the sediment dropped sharply into the overlying water, implying that microbes were actively oxidising methane and using it as an energy source. That is not photosynthesis, and it does not require sunlight. It is chemistry doing the work instead. Which means these lakes are not merely holes full of cold water, they are potential ecosystems powered by mineral reactions, buried carbon, methane cycling, and very patient microorganisms. Once that became clear, the lakes stopped looking like biological curiosities and started looking like laboratories. NASA's astrobiology coverage repeatedly draws the connection to icy moons such as Europa and Enceladus, not because Antarctica is secretly another planet, but because the same broad conditions recur: darkness, ice cover, liquid water below, and limited access to surface energy. If microbes can survive and cycle methane under Antarctic ice, then the basic idea of life in a buried ocean somewhere else in the solar system becomes easier to take seriously. That is one reason scientists have treated Antarctic subglacial lakes with such care. They are not just Antarctic stories, they are Earth-based tests of how little a living system may need in order to keep going. Then there is Lake Vostok, the giant in the room, although in this case the room is buried beneath nearly 4 kilometres of East Antarctic ice. NASA's 2022 astrobiology feature describes Lake Vostok as the largest known subglacial lake on Earth, and says it is thought to rank as the 16th largest lake in the world by surface area. The same source states that Vostok lies beneath about 4,000 metres of ice, and that some studies estimate it has been isolated from direct surface inputs for around 420,000 years. NASA's 2017 overview also notes that once scientists realised in 1994 that Vostok was about 500 metres deep, it became much more plausible as a habitable environment rather than merely a thin smear of meltwater. So Vostok is large, deep, pressurised, cold, and old enough to make ordinary human timescales feel rather flimsy. Vostok is also where caution becomes especially important, because it sits at the meeting point of genuine science and public imagination. It is tempting to treat it like a perfect lost world, sealed away since the age of mammals began, waiting under the ice with dramatic patience. The reality is more careful. NASA's 2022 piece says some estimates put the lake's isolation from direct surface input at around 420,000 years, while older NASA and NSF reports describe the broader system as potentially cut off for much longer, or discuss the possibility of unique ecosystems isolated for tens of millions of years. At the same time, evidence from accreted ice above the lake has been used to suggest microbes may be present, but direct access and contamination concerns have made firm conclusions difficult, so Vostok remains a place where the scale of possibility is enormous, but the most responsible science still speaks in measured sentences. That problem of contamination is not a side issue, it is central. If a lake has been isolated for hundreds of thousands or millions of years, and you arrive with drills, cables, warm water, instruments, and a long train of human microbes clinging to every imperfect surface, you can ruin the very thing you came to study. NASA's 2022 overview says new drilling technologies are being developed specifically to reach liquid water without contaminating it, and the BAS plan for Lake Ellsworth stressed that the entire drilling system had to penetrate 3 kilometers of ice without compromising the pristine lake below. BAS described Lake Ellsworth as a lake that could have been isolated from the rest of the biosphere for up to 500,000 years, and framed the entire effort as frontier science with engineering at the forefront. Antarctica does not merely ask whether you can reach a place. It asks whether you can reach it cleanly enough to deserve the answer. Lake Ellsworth is a useful reminder that some of the most interesting Antarctic habitats are known first as engineering problems. BAS's description of the site says the lake lies beneath about 3.2 kilometers of ice, is roughly 15 kilometers long and 3 kilometers wide, and was targeted because it offered the possibility of a relatively isolated freshwater environment in West Antarctica. That is the kind of place that immediately sharpens scientific thinking. If you find nothing living, that is informative. If you find microbes, that is informative in a much more cheerful way. Either result teaches you something about the lower limits of life and the kinds of energy pathways available in extreme environments. Yet even planning an attempt takes years, because every piece of equipment has to be designed around sterility, depth, pressure, and the simple fact that nothing in Antarctica happens with the sort of casual ease people enjoy in less unreasonable places. This is one reason the subglacial lakes have held scientific attention for so long. They force a person to think clearly about what life actually needs. They are dark. They are cold. Nutrient delivery is often limited. Photosynthesis is absent. Some are connected to wider water systems. Some may be much more isolated. And yet Lake Whillans showed that living cells and methane-cycling microbes can persist there, while Mercer and other active lakes show that buried water can also be part of a shifting continental drainage network rather than a static basin. Antarctica refuses the tidy choice between dead and teeming. Instead, it presents a set of habitats where life, chemistry, hydrology, and glaciology all overlap in forms that are both specific and inconveniently hard to observe. It also changes the meaning of the word lake. In ordinary use, a lake suggests surface water, open air, a shoreline. Perhaps an unfortunate goose with too much confidence. In Antarctica, a lake may be hidden beneath a kilometre or more of ice, invisible from above, known first by radar echoes or by subtle rises and falls in the ice surface detected from space. NASA's 2017 article explains that satellite laser measurements can reveal active lakes because the overlying ice slumps and rises as buried water drains and refills. The 2025 Nature Communications paper then turned that principle into a continent-wide update, identifying dozens of additional active lakes from elevation change patterns. So some Antarctic lakes announce themselves not with glittering water in the sun, but with the ice above them breathing very slowly over years. That is a pleasingly Antarctic form of visibility. The water is hidden, but the continent gives itself away in tiny motions if you watch carefully enough. It also means the lakes are not merely biological curiosities. They influence ice flow and can change how water moves under the ice sheet. NASA's 2022 feature says subglacial lakes play an important role in Earth's climate by influencing how ice flows into the ocean, and notes that a 2007 NASA study found this transport process could move enough water to matter for sea level. So buried lakes are not isolated side notes in the Antarctic system. They are part of the machinery of the ice sheet itself, which makes their study even more important and even more frustratingly difficult. There is also something quietly humbling about the scale of the unknown here. In 2017, NASA described Antarctica's subglacial lakes as one of Earth's final frontiers and said 402 had been confirmed at that time. By 2025, the continent-wide total had risen to 766. That is a large change in a relatively short scientific interval, and it suggests that the hidden water map beneath Antarctica is still being revised in earnest. When numbers like that shift, it is a sign that the story is not finished. The buried hydrological system is still revealing its outline, and every improvement in radar, altimetry, drilling, and clean access technology changes what can be asked next. What these lakes have shown so far is already enough to adjust the imagination. Water can remain liquid under crushing ice. Some lakes are ancient candidates for extreme isolation, while others are active parts of a continent-scale drainage system. Methane-eating microbes can live in dark sediments below 800 metres of ice. A lake like Mercer can be both hidden and comparatively young. A lake like Vostok can be enormous, deep, and old enough to make contamination control feel almost like a moral duty. And all of this is happening inside a continent most people still picture as little more than a frozen blank. Antarctica does not reward that kind of simplification. The closer you look, the more the interior starts to resemble a place with plumbing, chemistry, history, and biological possibilities rather than a giant white pause. And once you have followed the water this far beneath shelves across the seafloor, and now into lakes sealed under the continent itself, the next thought comes almost automatically. If life can persist in hidden Antarctic water that is dark, pressurized, cold, and starved of easy energy, then the real puzzle is no longer whether the continent contains living things in unlikely places. It plainly does. The harder question is how any organism, from a microbe to a fish to something stranger, adjusts its body to a world that seems designed to stop life at every turn. The answer begins with a correction. Antarctica does not defeat life simply by being cold. If that were true, the story would be over very quickly, and most of the continent's animals would have become little more than cautionary notes in evolutionary history. What the Antarctic actually does is force life into a narrower and stricter form. It rewards bodies that waste little, lose little, panic little, and improvise only when absolutely necessary. Animals that survive there do not overcome the environment in any heroic theatrical sense. They fit themselves to it so precisely that what would kill another creature becomes, for them, the normal background of existence. The Australian Antarctic Programme notes that Antarctic animals rely on both physical and behavioural adaptations to survive some of the coldest environments on Earth, while BAS describes many Southern Ocean species as highly specialised to a cold, stable world rather than broadly tolerant of many conditions. One of the simplest ways to understand this is to stop thinking of survival as one trick and start thinking of it as layers. First, there is the problem of heat, then the problem of freezing, then the problem of water loss, then oxygen, darkness, pressure, food shortage, breeding, and the basic nuisance of moving around in a place full of ice. Antarctic animals solve these problems in combinations. A seal does not survive the same way a fish does, and a fish does not survive the same way a tiny nematode in frozen soil does. Yet the general pattern is similar. Each species survives by giving up flexibility in exchange for efficiency. It is as though the continent has spent millions of years saying the same thing to every newcomer. Choose your method carefully, because there will not be much margin for error. For large warm-blooded animals, the first battle is simply not letting body heat leak away faster than it can be replaced. That is where blubber comes in. The Australian Antarctic Programme explains that whales, seals, and some penguins carry thick fat layers that act as insulation, trapping heat much as a blanket would, and that some species can also reduce blood flow to those outer layers to conserve heat. This means survival is not only about having insulation, but about managing circulation so the warmth stays where it is most useful. A creature in Antarctic air or water cannot afford to let its heat drift casually toward the surface. Its body has to treat warmth almost like money in a crisis, keeping a close hold of it and spending only what it must. Penguins add another layer to that economy. The same Australian Antarctic source notes that emperor penguins form dense huddles that can reduce heat loss by up to 50%, and that they also possess specialised nasal chambers and closely aligned arteries and veins that help recover heat lost through breathing and circulation. In other words, an emperor penguin does not merely stand there being thickly feathered and stoic. It is constantly using anatomy and group behaviour together, sharing warmth, sheltering from the wind, and recycling as much body heat as possible before that heat can escape into the Antarctic winter. The huddle is not a charming social preference. It is a survival device. The bird itself becomes part of the insulation system of the colony. That combination of anatomy and behaviour appears again and again in the south. On paper, one can describe an emperor penguin as a bird with special heat-saving structures. In practice, it is a bird that also knows when to compress into a living wall of bodies and when to rotate through the centre so no individual stays exposed too long. The elegance of Antarctic survival often lies there, in the way physiology and behaviour cooperate. A body may be built for cold, but it still behaves intelligently within cold. The environment is too severe for adaptation to remain theoretical. Every useful trait has to prove itself in daily life, in wind, darkness, and long breeding seasons on sea ice. For marine mammals, the problem changes the moment they dive. A Weddell seal is not just trying to stay warm, it is also trying to hunt beneath sea ice, hold its breath for long periods, and return to one of a limited number of breathing holes. The Australian Antarctic programme notes that Weddell seals live under fast ice and must breathe through cracks and holes, sometimes maintaining access with their teeth. Other Australian Antarctic material reports that they have about twice the blood volume per kilogram of body weight as humans, blood with about 1.6 times more hemoglobin, and oxygen stores in the blood up to roughly 3.5 times higher, with dives lasting up to 73 minutes. Scientific work on diving mammals broadly supports the same picture, showing enlarged blood volumes and high concentrations of hemoglobin and muscle myoglobin as core dive adaptations. Antarctic survival, in this case, is not only insulation, it is carrying your air reserve inside yourself in extraordinary amounts. That is an important distinction, because Antarctic life is often discussed as if cold were the single great challenge. It is not. Cold is simply the condition in which all the other problems occur. A Weddell seal needs blubber, yes, but blubber alone does not solve the difficulty of finding prey under ice, conserving oxygen, resisting pressure changes, and navigating back to a breathing hole before becoming a very sobering field note. The same animal survives because multiple systems cooperate at once. Insulation, oxygen storage, cardiovascular control, behaviour, memory, and a body shape suited for efficient underwater movement. In Antarctica, no single adaptation is enough for long. Survival tends to come as a bundle. Fish face an even less intuitive problem. In much of the Southern Ocean, seawater sits around -1.8 to -2 degrees Celsius, just above the freezing point of saltwater. B. Ayres and Smithsonian Ocean both note that Antarctic nototheniod fish survive these temperatures by using antifreeze proteins, or antifreeze glycoproteins, which prevent small ice crystals from growing into something fatal inside their bodies. Without that chemistry, many fish tissues would freeze, so instead of merely keeping warm, Antarctic fish prevent freezing from spreading. That is a very different kind of solution. A seal tries to remain internally warm. A cold-adapted fish accepts the ambient cold and changes the chemistry of its blood and body fluids so the cold cannot finish the job. Some of those fish go farther still. Smithsonian Ocean explains that Antarctic ice fish lack hemoglobin altogether, giving them pale or white blood, and peer-reviewed work on notothenioids shows that the cold, highly oxygenated and thermally stable Southern Ocean reduced the usual selective pressure for a more conventional oxygen transport system. This sounds absurd at first encounter, because hemoglobin is one of those biological features people assume vertebrates simply keep. Yet in a sea with high dissolved oxygen, and in animals with low metabolic demands, even such a basic assumption can be rewritten. Antarctica does that repeatedly. It takes traits that seem non-negotiable elsewhere and reveals that they were only non-negotiable under different conditions. There is a price for that precision though. BAS and other physiological studies emphasize that many Antarctic fishes are stenothermal, meaning they tolerate only a narrow temperature range. Their proteins, membranes and metabolic systems are optimized for a very cold, very stable sea, but that same specialization leaves them less flexible when conditions shift. This is one of the quiet truths of Antarctic adaptation. Extreme specialization can look like toughness, and in one sense it is. But it can also be a form of fragility. The animal is superbly fitted to one world and less able to cope when that world changes. The very adaptations that make survival possible can narrow the path of future survival. Smaller creatures often use a different strategy altogether. Instead of resisting freezing with insulation or specialized blood chemistry, they sometimes survive by managing water. BAS and related studies on the Antarctic nematode Panagrolimus davidi report that this tiny roundworm can survive extensive intracellular freezing and can also avoid freezing by cryoprotective dehydration, shedding water as surrounding ice forms. BAS has called it the best documented organism able to survive the disruptions brought about by total freezing. That is not merely hardy. It is biologically outrageous in the most respectable scientific sense. Rather than preventing the cold from entering its world, the nematode changes its own physical state so thoroughly that freezing becomes survivable. That strategy appears in other polar invertebrates too, including the Antarctic midge Belgica antarctica, whose larvae have been studied for their ability to endure dehydration-linked cold stress. The point is not that all these small animals do the same thing. It is that their scale allows solutions impossible for larger bodies. A penguin cannot simply dry itself into semi-suspended animation and wait for better weather. A nematode can do something disturbingly close to that. The Antarctic continent, especially in its soils and tiny ice-free pockets, is full of such creatures. Nematodes, tardigrades, mites, rotifers, springtails. The Australian Antarctic Programme notes that these are among the most common land animals in Antarctica. They do not dominate postcards, but they dominate many of the harshest habitats because being tiny allows a very different negotiation with cold, drought and freezing. Krill show yet another version of this logic. Noah's Ocean. Today explains that Antarctic krill can shrink their bodies and endure long periods of starvation, which helps them survive the winter months, and studies on krill ecology note their intimate relationship with sea ice, especially as habitat and protection during early development. This is a more ecological style of adaptation. Krill are not winning against winter by brute internal defences alone. They are also surviving by altering growth, energy use, and habitat use in step with the seasonal structure of the ice. A winter Antarctic animal often survives by becoming temporarily smaller, slower, less demanding, or more dependent on a very specific environmental niche. The lesson remains the same: waste as little as possible. The cold also changes the pace of life itself. BAS has reported that many Antarctic marine invertebrates use less energy for feeding, growth and reproduction than their relatives in warmer seas. That reduced pace is not laziness and not some charming side effect of living in a freezer. It is one of the most fundamental survival strategies available in a low-temperature world, because chemistry runs more slowly and food supply can be highly seasonal. An Antarctic benthic animal often survives by stretching its timetable. It grows more slowly, reproduces more slowly, and spends energy with exceptional restraint. If tropical life often looks exuberant, Antarctic life often looks economical. Its success lies not in speed, but in endurance. There are stranger outcomes as well. Some Antarctic invertebrates become unusually large, a pattern often discussed as polar gigantism. The University of Hawaii recently highlighted Antarctic sea spiders with leg spans of more than a foot, much larger than the tiny sea spider species people might imagine from other regions. Scientists are still working through the reasons different polar groups show this pattern, but cold water's high oxygen availability is often part of the conversation. Even here, though, size is only one piece of the story. Those sea spiders do not survive because they are giant. They survive because everything about their physiology, development and environment has been shaped together by a cold world over long time scales. Antarctica rarely gives a creature one miraculous gift. It usually rewires the whole arrangement. Vision, breathing, circulation, muscle chemistry, breeding behaviour, and even the timing of growth all get pulled into that rewriting. Research on Antarctic icefish vision notes that some species have evolved not only antifreeze systems and white blood, but also changes related to living beneath sea ice and in dim conditions. Emperor penguins are built to dive deeply, with the Australian Antarctic programme noting dives beyond 500 metres. Seals keep muscle oxygen bound in large quantities of myoglobin. Tiny terrestrial animals wait out desiccation and freezing in altered physiological states. Put all of that together and the pattern becomes very hard to ignore. Antarctic animals survive not because the environment is slightly less hostile than it appears, but because evolution has had enough time to turn hostility into a design constraint. There is also a quieter adaptation that matters just as much as any protein or fat layer, and that is timing. Antarctic animals often survive by doing things only when the environment gives permission. Breeding may be tied tightly to sea ice. Feeding may follow short seasonal booms. Growth may occur during narrow windows. Even under the ice, many animals rely on slow delivery of food from elsewhere, and on life cycles that match long intervals of scarcity. The Australian Antarctic Programme notes that almost all Antarctic plants and animals live in the very small fraction of the continent that is ice-free, while marine species are similarly concentrated where conditions allow. In such a world, success depends on reading the calendar of light, ice, food, and water with brutal accuracy. Miss the window, and physiology alone may not save you. That is why the phrase, "a world that should kill them," is only half right. By ordinary standards, yes, Antarctica should kill them, yet ordinary standards are built from ordinary places. The animals of the far south are not ordinary animals dropped accidentally into the wrong weather. They are lineages trained by millions of years of filtering pressure, stripped down to what works and burdened with the costs of that efficiency. The fish can stop ice from spreading through their fluids, but many cannot tolerate much warming. The seals can dive under ice for astonishing stretches, but only because their bodies are built around oxygen storage and control. The penguins conserve heat with extraordinary care, but depend on sea ice and colony behaviour. The nematodes can survive freezing and dehydration in forms that sound almost unreal, but only because their scale allows a solution no larger animal could copy. Every success is specific, every solution is narrow, and that specificity may be the most important thing to remember as we move farther into the hidden south. Antarctica is full of animals that have not conquered an impossible place so much as learned its exact terms. They survive by conserving heat, preventing ice growth, storing oxygen, reducing metabolism, shrinking through winter, drying out, huddling up, burrowing down, attaching themselves to the right surface, and waiting for the right season. Some are obvious enough to stand in documentaries. Many are so small or so concealed that a person could walk past their entire world without noticing. That difference in visibility has tricked us more than once. We are very good at noticing the emperor penguin and very poor at noticing the roundworm in frozen soil, but Antarctica does not rank them by charm. It ranks them by whether they work. Which brings us, almost inevitably, to the next difficulty. Even when animals have found workable ways to live in the south, Humans still have the separate problem of finding them. A creature may be alive, specialised, and firmly established in its habitat for thousands of years, and still remain nearly invisible to us if it lives under an ice shelf, inside dark water, deep on the seafloor, buried in sediment, locked in a subglacial lake, or simply in a place too remote and costly for people to reach often. The continent's animals have solved their side of the bargain. The more awkward truth is that we have not yet solved ours, which is why so much of Antarctica remains unexplored even now. That is the part many people underestimate. Antarctica remains unexplored not because scientists forgot about it, and not because no one has been interested enough to look. It remains unexplored because the continent is large, difficult, expensive, seasonally inaccessible, physically dangerous, environmentally protected, and in many cases hidden beneath ice that has to be crossed or drilled through before the real habitat even begins. On top of that, seen and mapped are not the same thing. NOAA notes that as of June 2025, only 27.3% of the global seafloor had been mapped with modern high-resolution methods, and explorers had visually seen less than 0.001% of the deep ocean seafloor. A place can appear on a map and still remain biologically unfamiliar. Antarctica is one of the best examples of that distinction. It helps to begin with size, because size quietly defeats a great many neat assumptions. Antarctica is not a remote research campus with a few icy roads and a politely labelled set of study sites. It is a continent covered by an ice sheet more than 4 kilometres thick in places, ringed by a stormy ocean, and full of regions where even reaching the starting point for science takes ships, aircraft, field camps, fuel depots, cargo planning, and favourable weather. British Antarctic Survey's guide for personnel going south describes Antarctica as the coldest, windiest, driest, and highest continent on Earth, notes that the sea around it is the world's stormiest, and says winter sea ice can expand to cover an area roughly the size of the continent itself. BAS's logistics summary for a major deep-field expedition adds that years of planning, intense international cooperation, deep-field camps, aircraft support, and large amounts of fuel, food, and equipment were required just to make the science possible. Exploration does not begin with looking. It begins with getting there alive and with enough supplies to keep the machines and people working. Then there is the simple fact that Antarctica is not accessible all year in the same way. Much Antarctic fieldwork happens during the austral summer, when there is continuous daylight in many regions, and travel is at least somewhat more manageable. The US Antarctic Programme's current field manual states that most fieldwork happens during the austral summer months, while the USAP participant materials note that additional temporary field stations are constructed and operated during that season. BAS's guide makes the other half of the point just as clearly. In winter, Antarctica is dark for many months. That seasonal structure means the working year is compressed. If weather turns, sea ice closes routes, or equipment fails during the usable window, an entire season can be damaged or lost. In easier parts of the world, a delayed trip may become next week's inconvenience. In Antarctica, it may become next year's project. The weather is not merely unpleasant, it actively interferes with navigation, visibility, safety, and sampling. The current USAP field manual says that in wind, fog, and snow, it is easy to become disoriented moving even between tents or huts at larger camps, and that visibility can plummet in minutes. The same manual notes that summer conditions on the peninsula can range from below -40 degrees Celsius to above freezing, with winds from light to sustained hurricane strength, and warns that wind chill sharply raises the risk of hypothermia and frostbite. Those are not background details. They explain why Antarctica cannot be explored quickly in the ordinary sense. A drone flight, a traverse, a boat operation, a sampling run, or a helicopter lift all depend on conditions that may stop cooperating with very little notice. Scientists do not simply arrive and start discovering things. much of polar work is waiting for the continent to permit a small amount of activity before it changes its mind again. Distance compounds everything. BAS notes that its research ship, the RRS Sir David Attenborough, is valuable precisely because it provides access to remote and challenging polar marine environments, and NSF's current Antarctic fieldwork solicitation makes plain that research requiring US Antarctic Programme logistical support is limited by what stations, vessels and support systems can actually provide. The solicitation says Antarctic fieldwork is supported only when it must be performed in Antarctica, and it also explains that current maintenance and upgrade work on Antarctic facilities places limitations on logistical support available for new projects. In other words, even before a scientist asks what lies under a shelf, in a trench, or beneath inland ice, there is a prior question. Can the transport, station capacity, aircraft, camp support, communications and safety systems carry that project at all? In Antarctica, the answer is often only partly, which means unexplored areas remain unexplored not through neglect, but through rationed access. That rationing becomes even more severe once the target lies away from established infrastructure. The US has 3 permanent year-round stations, and other national programs maintain their own bases, but that does not turn the continent into an evenly serviced grid. It creates a small number of footholds from which teams still have to push into enormous interior or marine spaces. BAS's AGAP logistics page shows how a single deep field campaign required 2 remote camps, multiple aircraft, extensive cargo preparation, snow school training, and transfer through South Pole Station before science teams could begin survey work. One can learn a lot from that example. The glamorous part of exploration is the moment a sensor records something new. The ordinary reality is that dozens of prior steps had to work first, including fuel distribution, camp siting, aircraft support, communications, acclimatization, and emergency planning. That level of effort is simply too costly and too slow to cover Antarctica evenly. The ice itself also hides what matters most. A great deal of Antarctic science is not conducted on open ground or open water, but through barriers. To study an under-ice shelf cavity, a subglacial lake, or the ocean floor beneath seasonal sea ice, researchers often need ships, sonars, hot water drills, boreholes, remotely operated vehicles, autonomous vehicles, and contamination controls. BAS's science strategy says satellites, sensors, autonomous vehicles, and AI are increasingly important for building digital models of the polar environment, and BAS's own guide says those tools have transformed what scientists can see. But those same sources also make clear that field observations remain essential. Satellites can reveal surface change, broad topography, and movement patterns. They cannot tell you what species are attached to a boulder 260 kilometers under an ice shelf, or whether a sediment core contains a previously undescribed invertebrate, or what a newly exposed seafloor community actually looks like. Technology narrows the mystery, but it does not remove the need for access. Antarctica remains unexplored partly because the most interesting habitats are often below the part remote sensing can easily observe. Even the seafloor, which people sometimes assume has now been thoroughly charted by modern systems, remains only partly known. NOAA says the entire seafloor has been mapped in a general way from satellites, but detail is limited and important features can remain unseen until high-resolution ship-based mapping is done. That limitation is more serious in Antarctica than in many lower-latitude oceans because ships cannot move freely through sea ice or around grounded icebergs. A 2025 Antarctic bathymetry study noted that extensive sea ice cover and stranded icebergs continue to make navigation difficult, leaving large Antarctic territories without direct seafloor soundings, while sub-ice shelf bathymetry is even harder and often requires seismic methods, boreholes, or autonomous vehicles. The study also reported that adequate mapping beneath ice shelves was available for only a small fraction of the larger shelves. So when scientists say parts of Antarctic marine habitats are unexplored, they are not speaking poetically. In many places, the shape of the bottom itself is still being revised. A second reason so much remains unexplored is that Antarctica is not merely remote. It is protected. The Protocol on Environmental Protection to the Antarctic Treaty designates Antarctica as a natural reserve devoted to peace and science, and Article 7 prohibits mineral resource activities other than scientific research. The Antarctic Treaty System also requires environmental impact assessment for proposed activities. The ATS Environmental Impact page states that Article 8 of the Protocol requires parties to conduct environmental impact assessments for Antarctic activities, with multiple levels of review depending on likely impact. If an activity may have more than a minor or transitory impact, additional evaluation is required, and draft comprehensive evaluations are made public and reviewed. This is a good thing. It slows people down for reasons that matter. But it also means Antarctic exploration cannot operate on a drill now apologise later model. In a place where hidden ecosystems may be uniquely isolated, scientific caution is part of the job description. That caution is especially important because many of the places most worth exploring are also the easiest to damage or contaminate. Under ice shelf communities, subglacial lakes, remote terrestrial microbial habitats, and long-lived benthic assemblages are not settings where one can be casual with waste, spills, camp placement, or dirty equipment. The USA Field Manual emphasises compliance with Antarctic Conservation Act protocols and any relevant protected area rules when selecting campsites, and it includes detailed requirements for communications, emergency supplies, spill reporting, and water reserves. BAS and NASA reporting on subglacial lake projects have likewise stressed clean access and contamination control. Antarctica therefore remains unexplored in part because serious exploration there must proceed carefully enough not to ruin the very thing it hopes to understand. That kind of science is slower by design, which is one of the reasons it is worth trusting when it does finally reveal something. Money and capacity also matter more than people often admit. A peer-reviewed PNAS commentary on Antarctic biorepositories put it bluntly. Access is a major impediment to scientific progress in Antarctica because extreme weather, remoteness, and inaccessibility make logistics extraordinarily challenging and expensive. That is not glamorous language, but it is honest. Ships capable of polar work are limited. Aircraft support is limited. Deep-field fuel and cargo are limited. Crew time, helicopter hours, drilling windows and available berths on station are limited. Antarctic science is therefore not constrained only by curiosity or scientific value. It is constrained by how much cold weather infrastructure the international research community can sustain in a place where every screw, tent pole, instrument case, and emergency ration has to be carried there on purpose. There is also the issue of human safety, which is less dramatic than in adventure stories and more controlling in reality. The USAP Field Manual requires daily check-ins, communications plans, emergency supplies, weather awareness, and survival provisions at camp. It warns that camps must maintain a 7-day emergency water supply and that wind can increase at any time. BAS's field guidance similarly emphasises that safety must come before everything else. This is another reason Antarctica does not yield to speed. A scientist in a temperate forest may stretch a field day a little longer and walk back to the vehicle in the rain. A scientist in Antarctica may be one storm shift away from a search and rescue problem. Entire ways of working that are normal elsewhere become irresponsible there. The continent is not just harder to explore than most places, it changes the acceptable ratio between curiosity and risk. And then there is a more subtle obstacle. Antarctica is not unexplored in the same way everywhere. Some places are observed often from space but rarely sampled directly. Some have good surface records but poor biological records. Some coastal areas are relatively accessible in summer, while the deep interior, The undersides of shelves, subglacial lakes, trench systems, and newly exposed seafloor remain much harder. BAS's own strategy points to integrated observations using satellites, sensors, autonomous vehicles, and AI precisely because no single method is enough. The result is a continent where knowledge is patchy rather than absent. One bay may be well studied, the next may be thinly sampled. One section of shelf may have repeated oceanographic records. A neighbouring under-ice cavity may have been seen only through one borehole. This patchiness can make Antarctica look more familiar than it is. We have many pieces, we do not yet have continuous coverage. That patchiness is why major discoveries can still appear in forms that feel almost old-fashioned. A drill hits rock instead of mud. A vehicle sent under ice finds a species field no one expected. A carved iceberg suddenly exposes a seafloor community that had been hidden for centuries. Those moments do not happen because Antarctic science is primitive. They happen because the ratio between total habitat and total direct observation is still very lopsided. NOAA's reminder that visual observation of the deep seafloor globally remains below 0.001% should cure anyone of the idea that hidden marine life is inherently improbable. Add sea ice, darkness, under-ice cavities, difficult weather and restricted access, and Antarctica becomes exactly the sort of region where reality can remain ahead of us for a long time. So much of Antarctica remains unexplored because every part of the problem stacks on top of the others. The continent is huge, the season is short, the weather is dangerous, the ocean is stormy, sea ice blocks access. The most interesting habitats are often below ice or below deep water. Mapping is incomplete, direct observation is rarer still. Environmental rules require caution. Logistics are expensive and limited. Safety planning consumes time and capacity. And even when all of that is solved for one field season, the result may still be only a few more holes, a few more dives, a few more transects, a few more samples from a place larger than most people can comfortably imagine. Antarctica is not unexplored because nobody bothered. It is unexplored because exploring it properly is one of the hardest kinds of work humans attempt on Earth. That is also why the unknown creatures matter. In a continent that has already been thoroughly searched, the idea of whole hidden communities would feel unlikely. In Antarctica, it remains entirely sensible. When access is this limited and direct viewing this sparse, the gap between what exists and what has been documented stays wide. The continent still has room for organisms that have been sampled but not recognised, imaged but not described, or never observed at all because the correct hole, dive, season, current, instrument, or stretch of exposed seafloor has not yet arrived. The mystery persists for practical reasons, not mystical ones, and that practical kind of mystery is often the most durable because it does not disappear when the lights come on. It disappears only hole by hole, dive by dive, sample by sample, while the ice keeps most of the map to itself. By the time science reaches the point of expecting unseen creatures, it is usually because the pattern has become hard to ignore. Antarctica is already giving us the clues. The deep southern ocean is still described in the research literature as largely unexplored, and expeditions there routinely recover samples in which the majority of species are new to science. A review of Southern Ocean Deep Benthos says, knowledge of that biodiversity is still scarce, while another study on Southern Ocean depth zonation states plainly that the deep Southern Ocean remains an unexplored wilderness where expeditions often bring up mostly new species. That is the first and most important reason scientists expect more hidden animals. The known record is not flattening out. It is still behaving like an incomplete inventory. That does not mean scientists are expecting some enormous dramatic beast to rise from under the ice and make everyone in the room spill their tea. The expectation is more disciplined than that. It is grounded in habitat size, sampling gaps, and repeated discovery of novelty. When researchers say Antarctica likely hides more creatures, they usually mean several different categories at once. More deep-sea invertebrates, more under-ice shelf specialists, more cryptic fish or range extensions that standard surveys have missed, and many more microbial lineages in subglacial systems. In some of those settings, the logic is simple. If you have an enormous habitat, very little direct sampling, and every new look keeps producing novelty, then it would be stranger if the unknowns had already run out. The first kind of expected but unseen life is probably the least glamorous in the public imagination and the most likely in reality. Small benthic animals living on or in the deep sea floor. The Southern Ocean Deep Benthos Review notes that the deep sea contains huge habitats, including abyssal plains, canyons, seamounts, reefs, vents and faults, and that more than 90% of species in many taxa from Southern Ocean deep samples were often new species at the time of collection, though that likely partly reflects undersampling. That is a remarkable statement. It suggests that when scientists sample the right place at the right depth, they are not adding a few final names to a nearly complete list. They are still encountering whole sets of organisms that had not yet entered the catalogue at all. So science expects more polychaete worms, more isopods, more crustaceans, more small mollusks, more foraminifera, more nematodes, and more assorted deep-bottom specialists, because the previous sampling history points strongly in that direction. This is especially true for animals that are poor dispersers or tied to particular bottom types. The same review notes that some Southern Ocean taxa include many species known only from that region, and it also emphasises how depth, sediment type, food supply, and geological structures shape biodiversity patterns. That means the unexplored seabed is not expected to hold a random blur of familiar global species. In many places it is expected to hold local or regional specialists, perhaps endemic ones, because the Southern Ocean's deep habitats are isolated in ways that promote distinct communities. In plain terms, if a canyon, ridge, vent field, or sediment basin has rarely been sampled, scientists do not expect it to be biologically generic until proven otherwise. They increasingly expect the opposite. A second category of expected but unseen life sits under the ice shelves, where the evidence is even more suggestive because the habitat is so large and direct observation has been so tiny. British Antarctic Survey describes floating ice shelves as the greatest unexplored habitat in the Southern Ocean, covering more than 1.5 million square kilometres of the Antarctic continental shelf. While only an area about the size of a tennis court had been examined through earlier boreholes when the Filchner-Ronner discovery was announced. At that site, researchers found stationary animals such as sponges attached to a boulder 260 kilometres from the open ocean in complete darkness, where filter-feeding communities had not been expected to persist so far beneath the shelf. BAS explicitly noted that the discovery raised questions about whether the organisms were new species and how common such life-covered boulders might be. That is the crucial point. Science now has enough evidence to expect that the first undershelf sessile community found is unlikely to be the only one. From there, the inference becomes fairly straightforward. If a single accidental borehole can find a hard substrate community that overturned earlier expectations, then similar hard substrate communities may exist elsewhere under shelves, especially where currents can deliver food and where rocks, drop stones, or other firm surfaces are available. Scientists are not guessing blindly here. They are following the logic of habitat repetition. Large undershelf cavities exist. Water circulates through them. Some places contain suitable attachment surfaces. At least one of those places supported sessile animals farther under the shelf than theory had predicted. Therefore, more such communities are reasonably expected, even if no one has seen them yet. That is not fantasy. It is what happens when one confirmed case forces the broader habitat to become newly plausible. There is also the matter of mobile animals under shelves. BAS's undershelf summary points out that earlier studies had already found some small mobile scavengers and predators in these habitats, including fish, worms, jellyfish, or krill, even before the sessile boulder community was documented. So the expectation now is not merely for more attached sponges or bryozoan-like communities, It is also for small roving animals using these dark cavities in ways still poorly characterised. The surprising part is not that mobility is possible under the ice. The surprising part is how little of that mobile fauna has been observed relative to the size of the habitat. If the largest unexplored habitat in the Southern Ocean has been sampled through a tiny handful of holes, then science has every reason to expect undershelf food webs that are still only partly outlined. A third category is microbial life in subglacial lakes and sediments, and here the expectation may be strongest of all. The 2025 single-cell genomic study from Subglacial Lake Mercer reports that microbes in that habitat are mostly novel and genetically isolated, with chemosynthetic and heterotrophic lifestyles shaped by oxygen availability. Earlier work on Lake Whillans found a microbial community distinct from drilling contamination and identified taxa associated with iron, sulfur, nitrogen, and methane cycling in a permanently dark ecosystem. Put those findings together and the implication is hard to miss. Scientists no longer treat subglacial lakes as places where life would be surprising. They treat them as places where life is likely to be chemically specialised, partly isolated and still underdescribed. The likely unseen creatures there are not fish or squid. They are lineages of bacteria and archaea, perhaps entire metabolic guilds, that no one has cultured yet and in some cases may not fit comfortably into existing ecological expectations. That microbial expectation grows even stronger when you remember how many hidden water bodies Antarctica appears to contain. ESA reported 85 new active subglacial lakes in 2025, increasing the known number of active lakes, while earlier NASA astrobiology work already treated Antarctica's subglacial lakes as an important analogue for life in dark icy environments. More lakes mean more environmental variety, different oxygen conditions, different sediment histories, different hydrological connections, different chemical gradients, and therefore different selective pressures. The Mercer Genomics paper's description of mostly novel, genetically isolated microbes suggests that each buried water system may not simply hold diluted versions of the same few organisms. Some are likely to hold distinct communities. So when science expects unseen life beneath the Antarctic ice sheet, it is often expecting microbial diversity first, because every new hidden lake or connected subglacial system adds another possible pocket of biological differentiation. A fourth category involves animals that are not entirely unknown as species, but are unseen in particular places, or undercounted because normal survey methods miss them. This is where environmental DNA begins to matter. A 2025 study using eDNA in the northern Antarctic Peninsula detected 32 fish species from water samples and recorded Pagonophrene albopina there for the first time, while the authors argued that eDNA could become a rapid and accurate monitoring tool for the Southern Ocean in areas with difficult logistics. That does not prove the existence of some dramatic invisible fauna. What it does show is that conventional observation has blind spots. Water can carry biological traces from animals that are rarely netted, filmed, or directly observed, so science expects more cryptic presences, more range extensions, and in some cases more species that have already been described somewhere but have not yet been seen in the Antarctic habitats where they actually occur. This is a subtle but important difference. Never seen does not always mean never existed in science before. Sometimes it means no person has directly observed the living animal in that setting, even though its DNA, fragments, or relatives are known. In Antarctica, where direct survey windows are so narrow, that distinction becomes very useful. Environmental DNA is not a magic trick, and its limits are real, but it changes the style of expectation. Scientists can begin to suspect hidden species assemblages before they have the footage to match. They can infer that a difficult channel, shelf edge, or seasonally inaccessible zone holds more fish diversity than trawls or cameras alone have shown. In a region where logistics routinely outrun observation, that kind of inference is not merely convenient, it is necessary. Then there are hydrothermal vents and other specialised deep-sea habitats, where the expectation is not just for more species, but for more odd species. Antarctic vent communities have already produced animals unlike those from vent systems elsewhere, including the now famous Antarctic Yeti crab. The Deep Benthos Review also emphasises that the deep sea includes geological structures such as vents, seamounts, canyons, and faults that support unique microbiological and faunal communities. Once such habitat variety is present, and once only a fraction of it has been thoroughly studied, science expects additional endemics and ecological specialists to turn up. Not because the phrase "lost world" makes a nice headline, but because isolated, chemically unusual habitats repeatedly generate their own local cast of organisms. Antarctica has already shown it can do that. There is no serious reason to assume it has only done so once. The same logic applies to meiofauna and sediment-dwelling animals, perhaps even more strongly than it does to the larger and more camera-friendly creatures. Tiny organisms that live between sediment grains within mud or in thin films on the seafloor are notoriously easy to miss and hard to identify. The Deep Southern Ocean Review treats meiofauna, macrofauna and megafauna together precisely because the smaller groups are an essential part of biodiversity patterns. In undersampled Antarctic environments, these tiny animals are likely among the richest sources of future discovery. They do not need giant size, dramatic anatomy, or perfect isolation to remain unseen. They only need a habitat few people core regularly, and a taxonomic group few laboratories can process quickly. Antarctica supplies both conditions very generously. There is another category science expects but cannot yet describe very well: hidden life stages. Eggs, larvae, juvenile forms, resting stages and seasonal appearances may all be present without having been matched to the right adults or observed in the right context. Antarctic biology is strongly seasonal in many places, and some habitats are accessible only briefly. That means scientists may know an adult species from one setting and still have never seen its eggs, nursery ground, winter behaviour, or dispersal stage in another. The deep and under-ice Antarctic remains particularly vulnerable to this sort of gap. The animal itself may not be wholly unknown, but its actual life in the habitat may still be invisible. In a place where even a newly exposed seafloor can reveal animals that had clearly been there for decades, hidden life stages are not a minor technical issue. They are part of why ecosystems can remain half understood for so long. This point is an inference from the repeated mismatch between sparse observation and high habitat complexity in Antarctic systems. Perhaps the most disciplined way to put all of this is that science expects more unseen Antarctic creatures wherever three conditions overlap: large habitat, little direct observation, and prior evidence of novelty. Deep Southern Ocean sediments meet that standard. Under-ice shelf cavities meet it even more strongly. Subglacial lakes and connected subglacial waters meet it for microbes. Vent systems and unusual geological habitats meet it for specialised endemics. eDNA, positive but visually undersampled regions, meet it for cryptic fish and invertebrates. The expectation is not one single dramatic discovery. It is a backlog of ordinary biological discovery waiting in extraordinary places, and that, in a way, is more interesting than a monster would be. A monster would be simple. One big reveal, one neat headline, one creature that lets people pretend the mystery has been solved because it had the decency to be large enough for the camera. Antarctica is not usually that cooperative. What science expects instead is a slower accumulation. More sponges where no sponges were expected, more worms and crustaceans from cores and trawls, more fish signatures in water samples, more metabolically unusual microbes in buried lakes, more localized species on slopes, seamounts, or vents, and more communities that force researchers to redraw the limits of where life can persist. The hidden south is likely full not of one answer, but of many small answers that have not yet met the correct drill hole, ROV, sediment core, or sequencing run. So when science says it expects creatures no human has ever seen, it is not speaking carelessly. It is reading the evidence the way a careful person reads footprints in snow. The steps are already there. Novel species keep turning up in undersampled deep habitats. Undershelf communities have appeared where earlier theory said they should not. Subglacial lake microbiomes contain mostly novel and genetically isolated organisms. eDNA is finding Antarctic fish diversity and range signals that direct observation alone had not captured. The only unreasonable conclusion at this point would be that the story is nearly complete. Far more likely is that Antarctica still holds many living things that no human eye has yet met directly, and that some of the most consequential discoveries ahead will look small on a screen, quiet in a core sample, and unmistakable only after the data has been checked twice, which leaves us with the final image hanging there in the dark. Not a dramatic beast waiting for applause, but a continent still moving, draining, freezing, melting, and circulating around habitats large enough to keep their inhabitants hidden a little longer. Somewhere under the shelves, in the sediments, in the trenches, or in buried water beneath the ice sheet, there are almost certainly organisms going about their work with no awareness at all that humans have started to guess they are there. And that is where the story naturally turns next, toward the simplest and strangest question of all. What, at this very moment, is still moving in the dark beneath the South Pole? And so we arrive at the question that has been waiting underneath all the others. After the ice shells, the buried lakes, the cold-adapted fish, the deep sea floor, and all the awkward, stubborn forms of life that keep appearing where they were not meant to, what still moves in the dark beneath the South Pole? The first answer is the least dramatic and in some ways the most important. Water moves. That may sound almost too obvious to mention, but in Antarctica the movement of hidden water is the reason so much else remains possible. Beneath floating ice shelves, seawater circulates through dark cavities that can stretch for vast distances. British Antarctic Survey has described these shelves as the greatest unexplored habitat in the Southern Ocean, and its reporting on life beneath them makes clear that these are not still sealed spaces. They are connected to the wider sea by currents that carry oxygen, salt, heat, and food. Even under immense ceilings of ice, the ocean is still in motion, and that movement is one of the reasons life can persist there at all. That matters because living things do not survive under Antarctic ice by magic. They survive because something reaches them. In open marine habitats, that something is often sunlight at the surface, followed by photosynthesis and the long ladder of a food web. Under thick ice shelves, sunlight does not arrive, but currents do. Those currents move particles, dissolved materials, and occasionally animals themselves through a world that would otherwise look impossible on paper. So before we even talk about fish or worms or anything stranger, it is worth remembering that the dark under the ice is not static. It has its own slow traffic. Cold water passes through. Food drifts in. Chemistry shifts. The habitat lives by movement even when human eyes are nowhere near it. Once that is understood, the next answer becomes easier. Small animals move there too, and we have known that in fragments for quite a long time. A 1979 report from the Ross Ice Shelf Project described baited traps and a camera lowered through the ice at a site 475 kilometres from the open Ross Sea and 597 metres below sea level. They found fish, many amphipods, and one isopod. Another report from the same project described scavenging amphipods, an isopod, and fish beneath 420 metres of ice and 430 kilometres from the open sea. Those are very plain scientific sentences, but they still carry a quiet force. Long before modern remote vehicles became common, dark-moving life was already present far under Antarctic ice. It was not abundant in the way a tropical reef is abundant, and it was not visible in the way a shoreline colony is visible, but it was there all the same, swimming or crawling in a place most people would have confidently called empty. The British Antarctic Survey later summarised the same general point even more broadly, noting that past studies beneath ice shelves had found small mobile scavengers and predators such as fish, worms, jellyfish, or krill. That list is a useful one because it reminds us that movement under Antarctic ice is not all of one kind. Some creatures drift, some pulse, some crawl over the bottom, some scavenge, some pass through the water column, some may spend only part of their lives there. The hidden south is not occupied by one lonely specialist and a lot of silence. It holds multiple kinds of motion, each adapted to darkness in a different way. There is also a particular pleasure in the fact that some of what moves beneath the ice does so in ways no one expected at all. Consider the sea anemone Edwardsiella andrilli, described from the underside of the Ross ice shelf after a robot called Skinny explored beneath it. The PLOS One species paper reports that this anemone lives with most of its column embedded in the ice shelf, with only its tentacle crown extending into the seawater below. It is, as the authors put it, the only known sea anemone reported to live in ice. That is an extraordinary sentence, and not just because it sounds like the punchline to a joke told by marine biologists who have been isolated too long. It means that even the lower boundary of the ice itself can host animals that move, feed, and maintain a hold on life in a place where no one had imagined such a lifestyle before. Its body remains mostly fixed, yes, but its tentacles still reach into the water below, feeding in the dark. So when we ask what moves beneath the South Pole, one answer is this: the tentacles of animals living upside down inside the ice, waving gently in black seawater beneath a frozen ceiling. That kind of answer changes the tone of the whole subject, because it shifts us away from the idea that hidden Antarctic life must always be large and spectacular to count. Sometimes what moves in the dark is a field of small tentacles, each one responding to flow. Sometimes it is an amphipod investigating carrion on the bottom. Sometimes it's a fish moving through water that sits near the freezing point of seawater. Sometimes it is krill drifting in from more open areas. The movement is often quiet, economical and easy to miss, which is one reason Antarctica has kept so much of it to itself. Human beings are not naturally talented at noticing low, steady, hidden life. We are much more drawn to things that leap at us or bite a camera. Antarctica, with its usual lack of cooperation, often offers the opposite. Then there are the places where the ice finally pulls back a little and lets us see what has been moving below for much longer than we have been present. In 2025, after Iceberg E84 broke away from the George VI ice shelf, an expedition aboard Falkor 2 reached newly exposed seafloor that had never before been accessible to humans. Schmidt Ocean Institute reported flourishing ecosystems down to 1,300 metres, including large corals and sponges that supported icefish, giant sea spiders, and octopus. Cambridge University, summarising the same work, described vibrant communities of ancient sponges and corals in the newly accessible region. That is one of those moments that makes the phrase "still moves in the dark" feel almost too modest. Because what was there was not just movement in the immediate sense, but persistence over decades or centuries, growth in hidden cold, feeding in darkness, and whole communities carrying on out of sight until one iceberg finally moved and allowed a look. Notice what that means. An octopus was moving there before the cameras arrived. Giant sea spiders were moving there before the cameras arrived. Icefish were moving there before the cameras arrived. Corals and sponges had been growing there before the cameras arrived. Human discovery did not begin the story. It merely interrupted our ignorance of it for a moment. That may seem obvious, but it is a helpful correction. Antarctica does not become alive when someone lowers an instrument. It was alive already. We simply notice late. The same applies to the microbial world beneath the ice sheet itself, though here the movement is of a different scale and kind. NASA's reporting on Lake Whillans described the first view below the ice of a microbial ecosystem, surviving in a deep, dark subglacial lake. The team drilled through about half a mile of ice, recovered water and sediment, and identified living cells in the samples, confirming that life can survive in those buried waters. A later NASA astrobiology feature on Antarctic subglacial lakes reported methane-eating microbes in the first sampling of a subglacial lake, and said DNA data suggested about 4,000 species. Those organisms are not swimming past cameras in a way that makes for dramatic documentary footage, But they are moving in the more fundamental sense. They metabolize, they divide, they cycle methane and other chemicals, they alter the environment around them while remaining almost entirely unseen. And if that sounds a little too microscopic to satisfy the question, it is worth remembering that on Earth, most of life's serious work is done by things we cannot comfortably see. Microbes moving through chemical pathways in total darkness may not look as impressive as an octopus drifting past a sponge garden, but from the standpoint of survival, they are every bit as consequential. In fact, one could argue that they are more so. NASA's astrobiology coverage of subglacial lakes and buried Antarctic water systems repeatedly treats them as models for how life might persist in dark, energy-limited places, not only on Earth, but on icy worlds elsewhere. The reason is simple. If something can stay alive there, beneath thick ice and without sunlight, then the lower limit for survival is farther down than people once assumed. That means what still moves beneath the South Pole includes not only animals we might someday film, but microbial economies we are only beginning to understand. Blood Falls offers perhaps the strangest example of all, because it gives us a visible leak from an invisible system. NASA explains that the red stain at Blood Falls comes from microbes living within a pool of ancient seawater trapped beneath Taylor Glacier for at least 1.5 million years. Another NASA astrobiology report says those microbes adapted to survive without enough light for photosynthesis by manipulating sulfur and iron compounds. So there, beneath Antarctic ice, what moves is not only water and cells, but chemistry itself, maintained by living processes across timescales that make ordinary human memory seem almost frivolous. One cannot help but admire the stubbornness of a microbe that spends 1.5 million years under a glacier handling iron in the dark, without once making a fuss about the conditions. It is also worth being honest about how little direct observation still exists. NOAA notes that humans have visually observed less than 0.001% of the deep ocean seafloor. A 2025 Science Advances results summarised through NOAA, and science says the same thing in slightly starker terms. Our visual coverage of the deep sea floor is tiny compared with the total habitat. Antarctica sits inside that global ignorance, and then adds its own barriers of sea ice, shelf ice, storms, darkness, and logistic cost. So when we ask what still moves beneath the South Pole, the only sensible answer is that known life is moving there, and unknown life almost certainly is too. We do not say that for effect. We say it because the ratio between habitat and direct observation remains so heavily tilted toward habitat that the hidden part of the story is still larger than the seen part. That unknown portion probably does not consist of one grand secret. It is more likely made up of many quiet ones. More deep-bottom invertebrates, more undershelf scavengers and filter feeders, more fish in places no net or camera has yet checked properly, more microbes in buried water systems, perhaps carrying out metabolisms no one has yet connected into a full ecological picture, more eggs, larvae, and life stages hidden in sediment, on rock or under ledges, more communities repeated in one cavity and absent in the next, because Antarctica is annoyingly fond of local conditions. Science has enough evidence now to expect those things, even if it cannot point to each exact species in advance. The Hidden South has earned that expectation, and so the answer to the chapter's question becomes both simpler and larger than it first sounded. What still moves in the dark beneath the South Pole? Water does. Amphipods do. Fish do. Jellyfish and krill likely do in some cavities. Sea anemone tentacles do from inside the ice. Octopus do where newly exposed seafloor reveals communities already in place. Giant sea spiders do across bottom habitats few people have seen. Microbes do in buried lakes and iron-rich brines, not by swimming theatrically through the gloom, but by continuing the patient work of metabolism in a world without sunlight. Whole ecosystems move there in the broader sense. As food arrives, bodies grow, cells divide, and generations replace one another with no audience at all. There is something deeply useful in that thought. We live in a time that encourages a rather childish confidence about what has already been found. There is a strong temptation to imagine that the Earth has now been fully checked, that mystery survives only in old stories or outer space, and that the remaining unknowns are merely technicalities waiting their turn in a spreadsheet. Antarctica is a good cure for that habit. It reminds us that reality can remain active without our supervision. The planet does not freeze in place simply because we have not looked closely enough. Beneath the ice, the biological day continues whether or not anyone records it. That continuity is, in its own way, more interesting than any sudden reveal. It also returns us to the very human side of all this. People often ask, in one form or another, whether there are still creatures on Earth no human has ever seen. Antarctica does not let us answer that with certainty in either direction, which is exactly why it remains so compelling. We know enough to say yes, probably. We know enough to suspect not only one or two species, but whole pockets of life still absent from direct observation. We also know enough to avoid becoming silly about it. The likely truth is not a single dramatic animal waiting for its entrance. It is a continent-sized collection of habitats where life persists beyond our routine gaze, in forms ranging from the almost invisible to the unexpectedly large. That really is mystery in its proper working condition. Not fantasy, not nonsense, just a gap between reality and the current reach of careful looking. So if you picture the far south now, perhaps do not picture only an empty sheet of white. Picture the moving water under that white. Picture a fish slipping through black cold below a shelf. Picture amphipods gathering where food has reached the bottom. Picture a field of small anemones set upside down into ice, their tentacles spread into the current. Picture microbes beneath a kilometre of ice, living on chemistry instead of sunlight. Picture an octopus crossing a seabed no person had seen until this decade, not because the darkness is magical, but because it is real, and reality has turned out to be busy down there, and somewhere beyond the last borehole, beyond the last camera cone, beyond the stretch of seafloor reached before weather closed in or fuel ran short, something else is almost certainly still moving too. Not for us, not toward us, just carrying on in the dark as it has been doing for a very long time,